Across the universe, certain discoveries completely change our understanding of energy and destruction. However, scientists have discovered a massive explosion that spread across millions of light years, releasing an enormous amount of energy from a galaxy cluster called Phoenix A, a black hole explosion so large that it surpassed all previous records in space. What triggered this extraordinary eruption, and what can it tell us about the powerful forces that shape our universe? Before we begin tonight's journey, like the video and comment below where in the world you're watching from and what the time is there now. We're always excited about hearing where our viewers are from. Phoenix. A galaxy cluster lies deep in the southern skies, in a part of space so distant that its light has taken billions of years to reach Earth. When astronomers look at Phoenix A, they are actually looking far back in time, to an era when the universe was much younger than it is today. The cluster is located in the constellation of Sculptor, a constellation that can be found in the southern celestial hemisphere. This vast region of galaxies is so far away that even with powerful telescopes it appears as a faint and distant collection of lights. Yet, beneath that faint glow lies one of the most active and energetic environments known to science. Phoenix A is not just a single galaxy, but a huge cluster containing hundreds of galaxies bound together by gravity. The combined mass of all the galaxies, stars, dark matter and hot gas within it makes it one of the most massive structures in the known universe. Astronomers estimate that the light from this cluster has been travelling toward us for about 5.7 billion years. That means when we observe it today, we're seeing it as it was more than halfway back to the time when the universe itself was formed, around 13.8 billion years ago. The Phoenix cluster, as it is also known, stands as a cosmic giant, both a relic of the early universe and an active site of tremendous energy and activity. The cluster gets its name Phoenix because of the constellation in which it resides, but in many ways the name also suits its remarkable nature. Like the mythical bird that rises from its ashes, the Phoenix cluster shows evidence of extraordinary rebirth and renewal processes on an intergalactic scale. Within it lies a massive central galaxy surrounded by an environment of superheated gas, swirling plasma and powerful radiation fields. These elements interact in ways that continually shape the cluster, leading to bursts of new star formation and gigantic outflows of energy from the supermassive black hole at its heart. At the very centre of the Phoenix cluster lies the galaxy known as the Brightest Cluster Galaxy, or BCG. This galaxy is so immense that it outshines all others within the cluster. Its core hosts a supermassive black hole, one of the most powerful ever detected. This black hole is not quietly sitting at the centre of the galaxy. It is actively devouring material and releasing enormous amounts of energy into its surroundings. Astronomers have discovered that the black hole in the Phoenix cluster is responsible for one of the most energetic outbursts ever recorded in the observable universe. The event is so intense that scientists describe it as a cosmic explosion of unimaginable scale, sending waves of energy rippling through space for millions of light years in every direction. To understand how extraordinary Phoenix A truly is, it helps to know that most galaxy clusters are relatively quiet in terms of star formation. In many clusters, the hot gas that fills the space between galaxies is so energetic that it prevents new stars from forming. This gas, known as the intracluster medium, is heated by shocks, collisions, and the energy released by black holes, and it usually remains too hot to cool down and condense into new stars. However, the Phoenix cluster breaks this rule. Observations made using some of the world's most advanced telescopes, such as the Chandra X-ray Observatory, the Hubble Space Telescope, and the Atacama Large Millimeter-Submillimeter Array, show that Phoenix A is undergoing an enormous burst of star formation. In fact, the rate of star formation in the central galaxy of Phoenix A is hundreds of times greater than that in our own Milky Way galaxy. While the Milky Way produces only a few new stars each year, the Phoenix cluster's central galaxy is forming hundreds of them. This astonishing level of activity suggests that the cooling gas in the cluster's core is condensing rapidly, feeding both the growth of new stars and the central black hole. Normally, the black hole's powerful energy outburst would heat up the surrounding gas and stop star formation, but in Phoenix A, this balance appears to be different. The energy being released seems to cool the gas in some regions while heating it in others, leading to a cycle of feedback that keeps both the black hole and star formation active at the same time. The cluster's structure itself is breathtaking. It stretches across millions of light years, with galaxies scattered throughout like glowing islands in a vast cosmic ocean. Between these galaxies lies a vast amount of hot gas that emits X-rays, which is how scientists first detected the cluster's full extent. The X-rays reveal that the intracluster medium in Phoenix A reaches temperatures of tens of millions of degrees Celsius, making it one of the hottest regions in the universe. Despite these extreme temperatures, the gas cools rapidly in the cluster's core, allowing it to condense and form new stars at a spectacular rate. This makes Phoenix A an exceptional laboratory for studying how galaxies evolve in such extreme environments. The distance to the Phoenix cluster also highlights just how immense the universe truly is. Light from the cluster has been travelling toward us for over 5.5 billion years, meaning that when that light began its journey, the solar system had not even yet reached its current form. Earth was already more than 4 billion years old, but the first multicellular life forms were still evolving in the planet's ancient oceans. By the time the light finally reached modern telescopes on Earth, humanity had developed the technology to explore the farthest reaches of space. The Phoenix cluster therefore gives scientists a glimpse of what the universe looked like billions of years ago, while also offering clues about its continuing evolution today. When astronomers study Phoenix A, they see not only a collection of galaxies but also a dynamic cosmic ecosystem. The galaxies within the cluster interact with one another through gravity, sometimes colliding or merging in spectacular displays. These interactions stir up clouds of gas, trigger waves of star formation, and feed the growth of supermassive black holes. In the Phoenix cluster, such processes are happening on an extraordinary scale. The central galaxy alone contains more mass than several trillion suns combined. Around it, smaller galaxies orbit and gradually merge, adding to the cluster's overall size and complexity. Over time, these mergers have helped build up the immense structure we now observe. The central black hole of Phoenix A is one of the most fascinating objects in all of astrophysics. It is estimated to have a mass of several billion times that of our Sun, and it is currently releasing energy at a rate that dwarfs anything seen in ordinary galaxies. This energy is released in the form of powerful jets of particles and radiation that shoot out from the black hole's poles, carving huge cavities into the surrounding gas. The scale of this outburst is staggering. Astronomers estimate that the explosion has released energy equivalent to hundreds of millions of supernovae combined. The shock waves created by this event have heated the cluster's gas and shaped its overall structure, creating enormous cavities that can be observed in X-ray images. Despite this violent activity, the Phoenix cluster remains surprisingly beautiful. High-resolution images reveal bright blue filaments of newly formed stars and glowing streams of gas that twist and flow around the central galaxy. These filaments stretch across hundreds of thousands of light years, forming delicate patterns that trace the motion of cooling gas as it falls inward toward the cluster's core. Such structures are rarely seen on this scale, making the Phoenix cluster a truly unique cosmic environment. The discovery of Phoenix A was a major event in modern astronomy. It was first identified through observations made by NASA's Chandra X-ray Observatory, which detected its exceptionally bright X-ray emission. The brightness of this emission immediately caught scientists' attention because it was far stronger than what they typically see in other galaxy clusters. Follow-up studies using optical and radio telescopes confirmed that the source was indeed a massive galaxy cluster, located billions of light years away. The data revealed not only the presence of a supermassive black hole, but also the extraordinary rate of star formation taking place within it. This combination of high-energy activity and rapid star birth made the Phoenix cluster one of the most remarkable discoveries of the 21st century. Since its discovery, the Phoenix cluster has been the subject of countless studies, each revealing new details about its structure and behaviour. Astronomers have used every available tool, from ground-based observatories in Chile and Hawaii to space-based telescopes orbiting Earth, to piece together its story. Observations in X-ray, optical, infrared, and radio wavelengths have helped scientists understand how its different components interact. These studies show that the cluster's environment is far from static. Instead, it is a dynamic and evolving system, shaped by both violent and creative forces. One of the most interesting aspects of Phoenix A is the balance between its heating and cooling processes. Normally, when a black hole releases so much energy, it prevents gas from cooling and condensing, effectively halting star formation. But in Phoenix A, the situation seems more complex. While the black hole's outbursts are indeed heating the gas, they are not completely shutting down the cooling process. This delicate balance allows parts of the gas to continue cooling and forming stars, even as other regions remain hot and turbulent. The result is a cluster that appears to be caught in a rare and temporary phase of intense activity, a kind of cosmic balancing act between destruction and creation. The Phoenix cluster also offers insights into the mysterious substance known as dark matter. Like all galaxy clusters, Phoenix A contains far more mass than can be accounted for by its visible galaxies and hot gas alone. Astronomers believe that most of its mass, over 80%, is made up of dark matter, an invisible form of matter that does not emit or absorb light, but exerts a powerful gravitational pull. By studying the motions of galaxies within the cluster and the way its gravity bends light from more distant objects, scientists can map the distribution of this dark matter. Such studies help researchers understand how galaxy clusters form and evolve under the influence of both visible and invisible matter. In addition to dark matter, the Phoenix cluster is rich in another mysterious form of energy: dark energy. This force, which drives the accelerated expansion of the universe, acts on cosmic structures like the Phoenix cluster over vast timescales. While dark energy cannot be observed directly, its effects can be measured by studying how galaxy clusters like Phoenix A are distributed throughout space. By comparing clusters at different distances, astronomers can trace how cosmic expansion has changed over billions of years, offering clues about the nature of dark energy itself. Thus, Phoenix A serves not only as a spectacular cosmic phenomenon, but also as a valuable scientific tool for probing the fundamental forces that shape the universe. The environment inside the Phoenix cluster is one of extreme conditions. The pressure, temperature, and radiation levels in its core are beyond anything that can be replicated on Earth. The intracluster medium, the hot gas filling the space between galaxies, is heated to temperatures of tens of millions of degrees, glowing brightly in X-rays. Embedded within this fiery plasma are cooler streams of gas that radiate in optical and ultraviolet light, revealing ongoing star formation. These contrasting regions, hot diffuse gas alongside dense cold filaments, illustrate the complex processes that drive the life cycle of galaxies. Because of its immense size and energy output, Phoenix A has become a key target for studying how supermassive black holes influence their surroundings. The central explosion in the cluster is not only the most powerful known, but also one of the clearest examples of how black hole activity can shape the large-scale structure of the universe. When a black hole feeds on infalling gas, it releases enormous energy in the form of radiation and high-speed jets. These jets can heat surrounding gas, push it outward, and even prevent further star formation by removing the raw materials needed to make stars. Yet, as Phoenix A demonstrates, this process is not always destructive. In some cases, the same energy that drives gas outward can also compress it in certain regions, triggering new waves of star formation. The study of Phoenix A continues to challenge and refine our understanding of how galaxies and galaxy clusters evolve. For decades, astronomers believed that massive clusters with active black holes would always suppress star formation, keeping their central galaxies relatively inactive. But the discovery of Phoenix A proved that this is not always the case. Instead, the cluster shows that under certain conditions, intense black hole activity can coexist with, and perhaps even encourage, massive bursts of star formation. This revelation has forced scientists to rethink how energy feedback works in the universe's largest structures. The Phoenix cluster's unusual properties also raise questions about how long such a phase can last. Astronomers believe that the current period of intense star formation and black hole activity is only temporary. Over time, the black hole's energy output may eventually heat the gas, enough to halt star formation entirely, leading to a quieter and more stable phase. But for now, Phoenix A remains in a rare and energetic state, giving scientists a rare opportunity to witness this cosmic transformation as it happens. Observations of the Phoenix cluster have revealed that it emits light across a wide range of wavelengths, from radio waves to X-rays. Each wavelength tells a different part of the story. Radio observations reveal the jets and bubbles created by the central black hole's outbursts. Optical observations show the stars and galaxies that make up the visible structure of the cluster. Infrared observations reveal the warm dust and cold gas associated with star formation, and X-ray observations show the distribution of the hot gas that fills the cluster's vast interior. By combining data from all these wavelengths, astronomers can build a detailed picture of how the cluster works. The Phoenix cluster is also a powerful reminder of just how small and fragile our own place in the universe really is. When we compare the size and energy of this colossal structure to our own Milky Way, the difference is staggering. The Milky Way spans about 100,000 light-years, while the Phoenix cluster stretches across several million light-years. The total mass of the cluster is thousands of times greater than that of our galaxy, and the amount of energy released by its central black hole dwarfs anything we can observe locally. Yet despite its immense scale, the Phoenix cluster is governed by the same physical laws that shape every part of the universe, from the smallest atom to the largest galaxy. The discovery and continued study of Phoenix A demonstrate the incredible power of modern astronomy. Using instruments capable of detecting faint light across vast cosmic distances, scientists have been able to uncover details about objects billions of light-years away. The combination of space-based observatories and ground-based telescopes has allowed researchers to piece together the story of how such a massive cluster formed, evolved, and continues to transform. Each new observation adds another layer of understanding, helping to explain not only the Phoenix cluster itself, but also the broader processes that govern the entire cosmos. The Phoenix cluster continues to captivate scientists because it challenges so many long-held assumptions. It shows that the relationship between black holes and star formation is not as straightforward as once thought. It reveals that galaxy clusters can experience dramatic bursts of activity, even at relatively recent cosmic times. And it provides a natural laboratory for exploring the physics of gas cooling, heating, and feedback on truly enormous scales. Every observation deepens the mystery, inviting further questions about how such powerful forces coexist in a delicate balance. The scale of time involved in studying Phoenix A is also awe-inspiring. The light we see from it today left the cluster long before human civilization existed, long before Earth had its current continents or climate. During those billions of years, the cluster itself has changed dramatically. Stars have been born and died, galaxies have merged and evolved, and the central black hole has gone through cycles of activity and dormancy. When astronomers observe Phoenix A, they are essentially looking back in time, witnessing events that happened when the universe was younger and more dynamic. Even now, as telescopes continue to observe Phoenix A, astronomers are discovering new details that reshape our understanding of cosmic evolution. Advanced instruments such as the James Webb Space Telescope are expected to provide even more detailed data, allowing scientists to study the cluster's galaxies and their formation histories with unprecedented clarity. These observations may reveal how the cluster's galaxies formed their stars, how the black hole grew so large, and how the balance between cooling and heating shaped its evolution. The Phoenix cluster stands as one of the brightest and most powerful X-ray sources ever found. Its discovery was a milestone in the study of galaxy clusters, showing that even in the vast and mostly empty expanses of the universe, there are places of extraordinary activity. The energy released from its center continues to shape the structure of the cluster, driving both destruction and creation in a continuous cycle. Every new piece of information gathered about it brings humanity closer to understanding the forces that govern not only this one cluster, but also the evolution of all galaxies and cosmic structures. Astronomers often refer to Phoenix A as a kind of cosmic laboratory because it allows them to test theories about how black holes and galaxies influence one another. By studying the cluster's radiation, structure, and composition, scientists can compare their observations with computer simulations of how such systems evolve over billions of years. These comparisons help refine our understanding of physics on the largest possible scales. The insights gained from studying Phoenix A extend far beyond this single cluster. They help explain how the universe itself has grown and changed since its earliest moments. In its vastness and energy, the Phoenix cluster tells a story of cosmic balance, where gravity, radiation, and matter continually interact in both harmony and tension. It reveals a universe that is not static, but alive with movement and transformation. Even across distances of billions of light-years, the forces shaping Phoenix A are the same ones that have influenced galaxies like our own. The cluster is a distant but profound reminder that the cosmos is filled with both mystery and order. chaos and beauty, destruction and creation, all bound together in the endless flow of time and energy that defines the universe itself. Long before the Phoenix Cluster was recognized, astronomers had already learned that clusters of galaxies were among the largest structures in the universe. A galaxy cluster is not just a single galaxy, but a massive gathering of hundreds or even thousands of galaxies, all held together by the force of gravity. Between those galaxies lies hot gas that emits powerful X-rays, invisible to human eyes but detectable with special instruments. In the 20th century, scientists began to explore this hidden universe through X-ray astronomy, which opened an entirely new window into space. During the 1960s and 1970s, astronomers first realized that many regions in the sky glowed faintly in X-rays. These X-rays were not coming from stars but from enormous clusters of galaxies, where the gas between galaxies reached temperatures of tens of millions of degrees. That discovery helped shape a new field of research, studying galaxy clusters through their X-ray emissions. Over time, telescopes became better, detectors became more sensitive, and the ability to see deeper into space improved dramatically. By the early years of the 21st century, space observatories like NASA's Chandra X-ray Observatory and the European Space Agency's XMM Newton telescope had begun to map the universe in X-rays with astonishing detail. These observatories could detect faint signals from billions of light years away. Around this time, astronomers were searching for distant galaxy clusters to study how the universe evolved. They wanted to understand how such massive structures formed and how supermassive black holes influenced their surroundings. In the year 2010, a team of scientists using data from several telescopes noticed something unusual in the southern sky. They were studying a region in the constellation of Phoenix, which lies in the southern hemisphere and is not visible from many northern observatories. When they analysed X-ray data from this region, they found an incredibly bright source that stood out sharply against the background. At first, they thought it might be an error in the data or a known object that had been mistakenly flagged as new. But as they continued to check the readings, the brightness and size of the object could not be explained away. The team then began comparing the X-ray data with optical and infrared images taken from other telescopes. What they saw was astonishing. The bright X-ray source was at the centre of a vast cluster of galaxies, one so large and luminous that it exceeded anything they had ever seen before. This was the Phoenix Cluster. It was located about 5.7 billion light-years away from Earth, meaning the light reaching us from it had started its journey when the universe was less than 2/3 of its current age. The Chandra X-ray Observatory played a major role in confirming the discovery. When astronomers pointed Chandra toward the Phoenix Cluster, the images revealed a massive cloud of hot gas surrounding the cluster. This gas was producing an enormous amount of X-rays, much more than any other known cluster at the time. The data showed that the Phoenix Cluster was cooling rapidly at its centre, which was unusual because most large galaxy clusters have mechanisms that prevent this cooling. The central galaxy of the cluster, Phoenix A, was also behaving in a very extraordinary way. Observations from the Chandra telescope, combined with images from the Hubble Space Telescope and radio data from the Very Large Array in New Mexico, revealed that the central region was bursting with activity. The galaxy was forming new stars at an incredible rate, around 500 stars every year, hundreds of times faster than what happens in our own Milky Way galaxy. This discovery was shocking because astronomers had believed that galaxies at the centres of such clusters usually had very little star formation. The reason behind this burst of star formation seemed to be connected to the cooling of the hot gas in the cluster. Normally in galaxy clusters, energy from a supermassive black hole at the centre prevents gas from cooling too quickly. The black hole sends out jets of high-energy particles that keep the gas hot and stop new stars from forming. But in the Phoenix Cluster, something different was happening. The central black hole appeared to be so active that it was releasing massive amounts of energy, yet somehow large quantities of gas were still cooling and forming new stars. This made Phoenix A an unusual and very important object to study. Astronomers used several instruments to analyse the cluster in different wavelengths of light. In X-rays, they could see the hot gas that filled the cluster. In visible light, they could see the galaxies themselves. In infrared light, they detected the newly formed stars and dusty regions where star formation was taking place. Each telescope provided a different piece of the puzzle. The discovery was officially reported in the year 2012, and the scientific community was quick to take notice. Researchers from many institutions, including the Massachusetts Institute of Technology, the University of Arizona, and NASA's Goddard Space Flight Center, collaborated to analyze the data. They described the Phoenix cluster as one of the most powerful and luminous X-ray clusters ever found. It was not only remarkable for its brightness, but also for what it revealed about the relationship between black holes and their environments. The Chandra X-ray data showed cavities or bubbles in the hot gas surrounding the central galaxy. These bubbles were created by the jets from the supermassive black hole. Such cavities are common in clusters, but in the Phoenix cluster they were much larger and more energetic. This meant that the black hole had released an enormous outburst of energy, possibly the largest ever recorded. This finding gave astronomers valuable insight into how black holes influence their surroundings on a cosmic scale. One of the fascinating things about the Phoenix cluster was how much information could be gathered from combining data across different wavelengths. For instance, observations from the South Pole Telescope had previously identified the cluster through something known as the Sunyaev-Zeldovich effect, a distortion in the cosmic microwave background radiation caused by the hot gas in clusters. This effect allowed scientists to find clusters regardless of their distance, as it depended on how the hot electrons in the cluster scattered background radiation from the early universe. The Phoenix cluster's strong signal in this effect was another indication of its enormous size and temperature. Further studies with optical telescopes confirmed that the cluster contained hundreds of galaxies bound together by gravity. The central galaxy, Phoenix A, was by far the largest, stretching over hundreds of thousands of light years. Spectroscopic observations allowed scientists to measure its redshift, a way of determining how far away an object is based on how much its light has been stretched by the expansion of the universe. The redshift measurement matched perfectly with the distance estimated from X-ray and microwave data, confirming the object's identity as a distant massive cluster. As scientists examined the Phoenix cluster in more detail, they realized it was not only extraordinary in brightness, but also in how fast its central region was cooling. The cooling rate of the gas was estimated to be around 3,000 solar masses of material every year. In most clusters, the energy from the central black hole balances this cooling process, but in Phoenix A, the balance appeared to have broken down. This made it a perfect natural laboratory for studying how black holes and galaxy clusters interact over time. The discovery of the Phoenix cluster showed that there are still extreme and unusual objects waiting to be found in the universe, even with all the advanced technology at our disposal. It demonstrated that while astronomers had developed general models for how galaxy clusters evolve, nature can always surprise us with exceptions. The intense star formation, the massive cooling flow, and the gigantic black hole outburst all made Phoenix A one of the most remarkable astronomical finds of the century. As the studies continued, astronomers wanted to understand why the Phoenix cluster behaved so differently from others. In many galaxy clusters, the energy from the black hole prevents large-scale cooling by stirring up the surrounding gas. But in Phoenix A, despite the powerful outbursts, cooling was still taking place. One possibility was that the outbursts were happening in cycles, powerful explosions followed by quieter periods when cooling could continue. Another idea was that the black hole's jets were not distributed evenly, allowing some regions of gas to cool faster than others. To explore these questions, scientists turned again to the Chandra X-ray Observatory and the Atacama Large Millimeter Submillimeter Array, ALMA, in Chile. ALMA's observations provided detailed maps of the cold molecular gas in the cluster's core. This gas was the raw material for star formation. The data showed that huge streams of cold gas were flowing inward toward the central galaxy, feeding both the starburst and the supermassive black hole. The interaction between the cooling gas and the black hole's feedback energy created a delicate balance that was still not fully understood. Astronomers also studied the Phoenix cluster using the Hubble Space Telescope, which revealed the structure of the galaxies in the cluster in visible and ultraviolet light. The central galaxy appeared filled with bright knots of young, massive stars surrounded by filaments of glowing gas extending tens of thousands of light years. These filaments resembled structures seen in other massive clusters, but were much more prominent and active in Phoenix A. The radio observations added another layer of detail. They showed evidence of powerful jets and radio lobes emerging from the central black hole. These structures extended for hundreds of thousands of light years and were responsible for the giant cavities seen in X-rays. The energy released by these jets was staggering, comparable to the total energy output of billions of stars over millions of years. Such power could only come from a supermassive black hole consuming vast amounts of matter and converting part of that energy into radiation and particle jets. It heats up and emits enormous amounts of energy, influencing the surrounding gas. The discovery of such a powerful system offered astronomers a rare opportunity to study how supermassive black holes grow and how they regulate the environments around them. The discovery of the Phoenix cluster was not a single moment, but rather a process that unfolded over several years of careful observation and analysis. Each telescope, each data set, and each team contributed pieces to the overall picture. The initial detection by the South Pole Telescope provided the first hint. The confirmation by Chandra revealed the X-ray power of the cluster. Optical and infrared images showed the galaxies and star formation. Radio data exposed the jets from the black hole. Together, these observations painted a full picture of one of the most dynamic and energetic regions in the known universe. The scientific excitement surrounding the Phoenix cluster did not fade after its discovery. In the years that followed, more detailed studies continued. Astronomers revisited the cluster using newer instruments and more advanced analysis techniques. They refined their measurements of its mass, temperature, and luminosity. They also explored how its properties compared to other massive clusters, such as the Perseus cluster and the Coma cluster. The Phoenix cluster outshone almost all of them in terms of X-ray brightness and cooling activity. Some researchers began to wonder if Phoenix A represented a temporary stage in the life of a galaxy cluster, a period of extreme activity that would eventually settle down. If that were the case, then perhaps all massive clusters might go through similar bursts at some point in their evolution. Observing such a phase in real time gave astronomers valuable clues about how cosmic structures change over billions of years. The discovery also prompted scientists to reconsider how feedback from supermassive black holes operates. The balance between heating and cooling in galaxy clusters is a key part of modern astrophysics. Too much heating, and star formation stops. Too little, and gas cools too fast, leading to massive bursts of star creation. Phoenix A seemed to be at the edge of this balance, showing both powerful heating from its black hole and intense cooling that fueled star formation. Understanding how these processes coexist became one of the main scientific goals in studying the cluster. In addition to scientific studies, the discovery of the Phoenix cluster captured public interest because of the sheer scale of its phenomena. The numbers involved were almost beyond comprehension. The cluster spans millions of light years across. The temperature of its gas reaches tens of millions of degrees. Its central galaxy alone contains trillions of stars, and new ones are being born at an incredible pace. The black hole in its core releases energy equal to hundreds of billions of suns. These facts reminded people of how vast and powerful the universe truly is. Over time, astronomers also began to detect faint signals of radio emissions and weak gravitational effects in the cluster that helped refine their understanding of its structure. Gravitational lensing, the bending of light from background galaxies due to the cluster's enormous mass, allowed scientists to map the distribution of dark matter within it. Like other galaxy clusters, the Phoenix cluster is composed mostly of dark matter, which provides the gravitational glue that holds it together. By analysing how background galaxies were distorted, researchers could estimate that dark matter made up the majority of the cluster's mass. This combination of visible matter, hot gas, dark matter, and the energy from the central black hole made the Phoenix cluster one of the most complex systems ever observed. It became a key target for many research programs seeking to understand the formation of large-scale cosmic structures. Each new observation added more depth to the story that began with its discovery in the early 21st century. Even years after the initial finding, the Phoenix cluster continued to reveal new surprises. Later analyses found evidence that the energy released by the central black hole might have created shockwaves traveling through the cluster's hot gas. These waves carried enough energy to heat the surrounding material and possibly regulate the cooling flow over long timescales. Such findings helped connect the behavior of Phoenix A to other well-known systems, showing that while it was extreme, it still followed some universal physical laws governing how black holes and galaxies interact. The discovery process also highlighted how collaboration and technology have transformed astronomy. No single telescope or instrument could have identified the Phoenix cluster alone. It required data from X-ray observatories, microwave detectors, optical telescopes, and radio arrays. Each technology contributed its strengths. X-rays revealed the hot gas, microwaves traced the cluster's impact on the cosmic background, optical images showed galaxies, and radio waves exposed the activity of the black hole. The teamwork of scientists across different countries and institutions turned scattered signals into a coherent picture of one of the universe's grandest structures. The name Phoenix Cluster itself was fitting for such a discovery. It referred not only to its position in the constellation of Phoenix, but also symbolized rebirth and power, echoing the mythical bird that rises from its own ashes. In a sense, the name represented how the cluster's central galaxy was constantly renewing itself through star formation, even as it was shaped by the destructive power of its black hole. Astronomers continue to observe the Phoenix Cluster with new generations of telescopes, including the James Webb Space Telescope, which can study its infrared light with unprecedented detail. These ongoing observations help scientists look even further into the cluster's history, tracing how its galaxies formed and evolved. The Webb telescope's ability to detect faint infrared light allows researchers to peer through the dust and gas that hide some of the most active regions of star formation in Phoenix A. As technology advances, future missions may provide even clearer views of the processes that first brought the Phoenix Cluster to human attention. High-resolution X-ray observatories planned for the coming decades will allow astronomers to map the hot gas more precisely, identifying shock fronts, cavities, and turbulence with greater accuracy. Radio telescopes like the Square Kilometre Array will provide sharper images of the black hole's jets, helping to measure how often and how powerfully it erupts. The journey that began with a faint X-ray signal in the southern sky has grown into one of the most detailed and enlightening studies of a galaxy cluster ever undertaken. The discovery of the Phoenix Cluster not only revealed an extraordinary object, but also demonstrated how far humanity's tools for exploring the universe have come. It is a reminder that even in the vastness of space, hidden wonders are still waiting to be found by those who know how to look deeply enough. Through decades of patient observation, comparison, and collaboration, astronomers pieced together the remarkable identity of Phoenix A, an enormous cosmic system glowing brightly in X-rays, filled with galaxies, star formation, and a black hole of unimaginable power. From its first detection in the early 2010s to the ongoing studies that continue today, the discovery of the Phoenix Cluster stands as one of the most significant achievements in modern astronomy, showing that the universe always has more to reveal to those who search the skies with curiosity and determination. A galaxy cluster can be thought of as a cosmic city filled with galaxies instead of buildings. Each galaxy in a cluster can contain billions of stars, planets, and clouds of gas and dust. Between these galaxies lies a very thin but extremely hot gas called the intracluster medium, which can reach temperatures of tens of millions of degrees Celsius. This gas is so hot that it emits powerful X-rays, which scientists detect using special space telescopes. Even though this gas is extremely thin, it actually makes up a significant part of the cluster's total visible mass. Yet, when astronomers measure how galaxies move within a cluster, they find that there must be far more mass present than what can be seen in the galaxies and hot gas. This missing mass is what scientists refer to as dark matter, a mysterious and invisible substance that makes up most of the cluster's total weight. The formation of galaxy clusters is a long and complex process that began not long after the Big Bang, which occurred around 13.8 billion years ago. In the early universe, matter was spread almost evenly everywhere, but tiny irregularities existed in this otherwise smooth sea of particles. Over time, gravity began to pull slightly denser regions together, slowly drawing in more and more matter. These small clumps of matter grew larger and denser, eventually forming the first stars and galaxies. As the universe aged, galaxies began to gather into groups and then into even larger structures known as clusters. The process of forming a cluster takes billions of years, involving countless collisions, mergers, and gravitational interactions among galaxies and the dark matter surrounding them. The early stages of galaxy cluster formation likely started when small groups of galaxies, called protoclusters, began to merge together. These protoclusters were regions in the young universe where gravity was particularly strong, pulling galaxies, gas, and dark matter toward a common center. As these regions accumulated more matter, their gravitational attraction became stronger, allowing them to pull in even more galaxies and gas from the surrounding space. Over hundreds of millions of years, these merging groups created enormous structures that we now recognize as fully developed galaxy clusters. Even today, clusters continue to grow by attracting additional galaxies and smaller groups through gravity, making them dynamic and constantly evolving systems. Galaxy clusters vary greatly in size, shape, and composition. Some contain only a few hundred galaxies, while others can host several thousand. The largest ones, known as superclusters, can stretch for hundreds of millions of light-years across space, containing multiple clusters bound together by gravity. Within a typical cluster, galaxies move at incredible speeds, sometimes thousands of kilometers per second, as they orbit around the cluster's common center of mass. These fast motions help keep the cluster stable against collapse, balancing the inward pull of gravity with the outward motion of the galaxies and hot gas. Astronomers use several methods to study galaxy clusters and understand their properties. One of the most important techniques involves observing X-rays emitted by the hot gas between galaxies. Telescopes such as the Chandra X-ray Observatory and XMM Newton have provided detailed images of this glowing gas, revealing the structure and temperature of clusters. By studying the distribution of this gas, scientists can infer how much total mass the cluster must have to hold the gas in place. Another powerful method is gravitational lensing. Because galaxy clusters are so massive, their gravity can bend the light coming from distant galaxies behind them, distorting and magnifying the background light. This effect, predicted by Einstein's theory of general relativity, allows astronomers to measure the cluster's total mass, including the dark matter that cannot be seen directly. Dark matter plays a crucial role in the formation and stability of galaxy clusters. Although it does not emit, absorb, or reflect light, it makes up about 80 to 90% of a cluster's total mass. Without dark matter, the visible galaxies and hot gas would not have enough gravity to stay bound together. Scientists believe that dark matter began clumping together very early in the history of the universe, long before galaxies even formed. These dark matter clumps acted like cosmic seeds, attracting normal matter toward them through gravity. Over time, these regions grew larger and denser, forming the scaffolding upon which galaxies and clusters eventually took shape. The galaxies within a cluster come in various types and sizes. Many of them are large elliptical galaxies, which tend to dominate the central regions of clusters. These elliptical galaxies are often older, containing mostly red stars and very little gas or dust for new star formation. In contrast, spiral galaxies, which are rich in gas and actively form new stars, are more common near the outer parts of clusters. This difference arises because the dense environment inside a cluster can strip away the gas from galaxies as they move through the hot intracluster medium. This process, known as ram pressure stripping, removes the fuel needed to form new stars, gradually turning once active spiral galaxies into more passive elliptical ones. At the very heart of most clusters lies a massive central galaxy, often called the brightest cluster galaxy or BCG. These galaxies are much larger and more luminous than typical ones, sometimes containing trillions of stars. They likely grow to such enormous sizes by merging with smaller galaxies that fall toward the cluster's center over time. Many of these central galaxies also host supermassive black holes, which can release enormous amounts of energy when they consume surrounding gas. This energy can heat up the intracluster gas, preventing it from cooling and forming new stars. The balance between this heating and cooling shapes the overall evolution of the cluster and influences how galaxies within it develop. The hot gas between galaxies in a cluster is one of its most striking features. Even though this gas is extremely thin, much less dense than the best vacuum humans can create on Earth, its sheer volume makes it incredibly massive. This gas contains not only hydrogen and helium, but also heavier elements such as iron, oxygen, and silicon, which were produced by supernova explosions in the galaxies. Over billions of years, these elements have been ejected into space by stellar winds and exploding stars, enriching the cluster's environment with chemical ingredients that future generations of stars can use. The temperature of the intracluster gas can reach tens of millions of degrees Celsius, causing it to emit X-rays that space telescopes can detect. These X-rays reveal intricate structures within the cluster, such as shock waves created by galaxy collisions or by jets of material ejected from active black holes at the centers of galaxies. These shock waves can heat the surrounding gas, stir it up, and even affect how galaxies form stars. By studying the patterns and variations in X-ray brightness, astronomers can map the distribution of matter and energy across the cluster and learn about the powerful forces that shape these enormous systems. One fascinating aspect of galaxy clusters is that they continue to change over cosmic time. Clusters are not static. They are still growing as gravity pulls in more galaxies and dark matter from their surroundings. When two clusters collide, the event releases an incredible amount of energy. The galaxies themselves usually pass by each other because they are separated by vast distances, but their surrounding gas clouds collide and heat up dramatically. This process can create huge shock waves and turbulence in the intracluster medium, altering its temperature and structure. Some of the most spectacular cosmic events ever observed are cluster mergers, which can take billions of years to complete. A famous example of a cluster collision is the Bullet Cluster, located about 3.7 billion light-years away. Observations of this system have provided some of the strongest evidence for dark matter. In the Bullet Cluster, astronomers found that the majority of the mass is not located where the hot X-ray emitting gas lies, but rather in regions traced by the gravitational lensing effect. This means that while the normal matter, the hot gas, slowed down and heated up during the collision, the dark matter passed through almost unaffected. Such observations confirm that dark matter behaves differently from ordinary matter and does not interact with light or normal particles in the usual way. Studying clusters also allows scientists to measure key properties of the universe itself. Because clusters are so massive and widespread, their number and distribution across cosmic time provide clues about how the universe has expanded and evolved. By counting how many clusters exist at different distances, astronomers can test theories of cosmology, including the effects of dark energy, the mysterious force that is causing the universe to expand faster and faster. In this way, clusters serve as cosmic laboratories for studying both visible and invisible components of the universe. The light from galaxy clusters can also travel across billions of light-years before reaching Earth. Since light takes time to travel, looking at distant clusters is like looking back in time. The most remote clusters we can see formed when the universe was only a few billion years old. Observing them allows scientists to witness how clusters looked in their early stages, helping them understand how these colossal systems evolved from small groups of galaxies to the giant structures we see today. Space telescopes such as the Hubble Space Telescope, the James Webb Space Telescope, and various X-ray observatories have provided detailed images of these distant clusters, showing that even at early times, the universe was already forming large, complex structures. In addition to galaxies and gas, clusters are also home to numerous smaller structures, such as dwarf galaxies and globular clusters. Dwarf galaxies are much smaller than normal ones, often containing only a few million stars, but they are abundant within clusters. Many of them are thought to have been stripped of their gas and stars by gravitational interactions with larger galaxies. Globular clusters, on the other hand, are dense collections of old stars that orbit within and around galaxies. They serve as fossils of the early universe, offering clues about the conditions in which the first stars formed. Interactions among galaxies in a cluster are frequent and intense. As galaxies move through the cluster, they experience powerful gravitational forces from their neighbours and from the cluster as a whole. These forces can distort galaxies, pulling out long tails of stars and gas in spectacular displays known as tidal interactions. When galaxies pass very close to one another, they can even merge, creating larger galaxies and triggering bursts of new star formation. Such encounters are more common in the crowded cores of clusters, where galaxies are packed closely together. However, over time, the repeated interactions and the stripping of gas tend to shut down star formation in many cluster galaxies. As a result, clusters are often dominated by red, old galaxies with little ongoing star formation. This makes the centers of clusters relatively quiet and stable regions compared to the more active outer areas, where new galaxies continue to fall in and fresh material can still fuel some activity. The gravitational potential of a galaxy cluster is so deep that even light struggles to escape its influence. This causes the phenomenon of gravitational redshift, where the light leaving the cluster loses a tiny bit of energy, stretching its wavelength slightly toward the red end of the spectrum. Although this effect is very small, it can be measured with precise instruments and provides another way to study the cluster's mass and structure. In addition to X-ray and optical observations, astronomers also study clusters through the Sunyaev-Zeldovich effect, named after the scientist who predicted it. This effect occurs when the hot electrons in the intracluster gas interact with the cosmic microwave background radiation, the leftover glow from the Big Bang. The interaction slightly changes the energy of the background photons, creating a subtle distortion in the radiation that can be detected by sensitive radio and microwave telescopes. Measuring this effect allows scientists to estimate the total amount of hot gas in a cluster and, combined with other data, helps determine its overall mass and distance. Clusters of galaxies are not isolated structures, they are part of an even larger cosmic network called the cosmic web. This web is made up of vast filaments of dark matter and gas that stretch across the universe, connecting clusters and superclusters over immense distances. Between these filaments lie enormous voids, where very few galaxies exist. The cosmic web gives the universe its large-scale structure, and galaxy clusters sit at the intersections of these filaments, acting as massive knots where matter has gathered over billions of years. Studying how clusters are connected to the cosmic web helps astronomers understand how matter flows across the universe. Gas and galaxies move along the filaments toward clusters, feeding them and allowing them to grow. This cosmic flow of material continues even today, showing that the universe remains dynamic and ever-changing. Observations and computer simulations together reveal that the pattern of clusters and filaments we see today formed from the tiny density fluctuations that existed shortly after the Big Bang. Computer simulations have become an essential tool for understanding galaxy cluster formation. By using powerful supercomputers, scientists can model how dark matter, gas and galaxies interact over billions of years. These simulations start with conditions similar to those of the early universe and follow the evolution of matter as it forms clusters, galaxies, and other structures. The results often match what is observed in the real universe, giving researchers confidence in their understanding of cosmic evolution. However, simulations also reveal the complexity of these processes, showing that feedback from black holes, star formation, and supernova explosions all play vital roles in shaping the properties of clusters. One striking feature revealed by both observations and simulations is the role of feedback from active galactic nuclei, the regions around supermassive black holes in the centers of galaxies. When these black holes pull in gas, they can release enormous amounts of energy in the form of radiation and powerful jets. These jets can extend for hundreds of thousands of light years, pushing aside the surrounding hot gas and creating vast cavities in the intracluster medium. This process can prevent the gas from cooling too quickly, thereby regulating the rate of star formation in the cluster's core. Such feedback mechanisms are now recognized as crucial in maintaining the balance between cooling and heating in clusters. Galaxy clusters also contain relics of past events, in the form of radio halos and relics. These are large regions of diffuse radio emission that indicate the presence of high-energy electrons and magnetic fields within the intracluster medium. Radio halos are usually found near the center of clusters and are associated with turbulence caused by mergers. Radio relics, on the other hand, are found near the outer edges of clusters and are thought to trace shock waves created by large-scale collisions. These radio features help astronomers study the magnetic and energetic environment of clusters, adding another layer to the complex story of how they form and evolve. Clusters serve as natural laboratories for testing the laws of physics under extreme conditions. The temperatures, densities, and energies present in clusters cannot be replicated on Earth, yet they allow scientists to explore how matter behaves under such circumstances. By comparing observations of clusters to theoretical predictions, researchers can test models of gravity, particle physics, and cosmology. In particular, galaxy clusters provide strong evidence for the existence of both dark matter and dark energy, two mysterious components that together make up about 95% of the total content of the universe. In the modern era of astronomy, surveys that scan large portions of the sky have allowed scientists to discover and study thousands of galaxy clusters. These surveys combine data from optical telescopes, X-ray observatories, and microwave instruments to build comprehensive catalogues of clusters across different distances and epochs. With each new discovery, astronomers gain more insight into how matter has gathered and evolved since the universe's earliest days. Future missions and observatories are expected to deepen this understanding even further, allowing us to trace the growth of cosmic structures from the smallest galaxies to the largest clusters and superclusters spanning hundreds of millions of light years. Supermassive black holes are among the most powerful and mysterious objects in the entire universe, and their presence lies at the heart of almost every large galaxy ever observed. These colossal bodies are millions, and sometimes even billions, of times more massive than the Sun. Their immense gravity is so strong that not even light can escape from within a certain distance known as the event horizon. For many years, astronomers once thought that black holes were simply destructive cosmic traps swallowing everything around them. But as our understanding has grown, it has become clear that supermassive black holes are far more than just cosmic monsters. They play a deep and complex role in shaping the galaxies and galaxy clusters they inhabit. In many ways, these immense objects are both creators and regulators, influencing the growth of galaxies, the motion of stars, and the temperature of the hot gases that fill the vast spaces between them. At the center of most galaxies, including our own Milky Way, there is a supermassive black hole. The one in our galaxy is called Sagittarius A, and it has a mass of about 4 million suns. However, in some of the largest galaxies within galaxy clusters, the black holes are hundreds or even thousands of times more massive. For instance, the black hole in the giant galaxy known as Messier 87, which lies in the Virgo cluster, has a mass close to 6.5 billion suns. When these gigantic objects feed on gas, dust, and even stars, they release enormous amounts of energy. This process does not simply vanish into the darkness, but instead floods the surrounding region with radiation and powerful jets of charged particles that shoot out at nearly the speed of light. The energy from such activity can travel across entire galaxies and sometimes even reach into the surrounding cluster environment. The space within a galaxy cluster is filled not just with galaxies, but also with a thin gas known as the intracluster medium. Though this gas is extremely sparse, it is heated to tens of millions of degrees and glows brightly in X-ray light. The reason for this heat is connected to both gravity and the activity of the supermassive black holes found at the centers of the cluster's largest galaxies. The black holes do not remain silent. They constantly interact with this hot gas, preventing it from cooling too quickly and collapsing into new stars. Without this effect, the gas might cool down, flow toward the cluster's center, and trigger a burst of star formation. Instead, the energy released by the black hole acts like a heater, keeping the gas hot and stable. Astronomers call this feedback a process where the black hole regulates its surroundings through its energy output. One of the most striking examples of this feedback can be seen in galaxy clusters like Perseus, Phoenix, and Virgo. Observations with space telescopes such as the Chandra X-ray Observatory and the XMM Newton have shown enormous cavities, bubbles, and shock waves in the hot gas that surrounds the central galaxies. These cavities are not empty. They were carved out by jets of high-energy particles ejected from the supermassive black hole's accretion disk. The material spiraling into the black hole creates strong magnetic fields, and these fields channel part of the energy outward in narrow collimated jets that can travel hundreds of thousands of light years. As these jets push through the hot gas, they displace it and create vast balloon-like structures filled with radio-emitting plasma. The amount of energy required to create such cavities is mind-boggling, in some cases equivalent to the energy released by hundreds of millions of supernova explosions. The balance between heating and cooling is one of the most important roles played by supermassive black holes and galaxy clusters. When the black hole is inactive, the hot gas in the cluster's center begins to radiate energy and cool down. As it cools, it condenses and begins to flow inward, feeding the black hole and triggering a new burst of activity. The renewed energy output then reheats the gas, stopping the cooling process once again. This cycle repeats over and over, creating a delicate equilibrium that can last for billions of years. Without this regulation, galaxy clusters would look very different. They would be filled with large numbers of young, bright stars forming in great bursts near their centers. Instead, most cluster cores are dominated by old stars and giant elliptical galaxies that have long since ceased to form new ones. In addition to heating the gas, supermassive black holes also affect how galaxies move and evolve within clusters. The gravitational pull of the cluster itself keeps the galaxies bound together, but the central black hole influences the immediate region around it. In some cases, its immense mass can cause stars and gas to move in particular patterns, forming disks or jets that stretch across thousands of light years. When two galaxies merge, their central black holes eventually spiral toward each other and merge as well, releasing a tremendous burst of gravitational waves that ripple through space-time. Such mergers are thought to be one of the main ways that black holes grow to their immense sizes. Each time galaxies collide, the new combined galaxy inherits a larger and more powerful central black hole, capable of releasing even greater amounts of energy into its surroundings. The relationship between a galaxy and its central black hole is not one-sided. Studies have shown that the mass of a supermassive black hole is closely connected to the total mass of stars in its host galaxy's bulge. This connection, known as the M-sigma relation, suggests that galaxies and black holes grow together. When the black hole is feeding rapidly, it can produce a bright active galactic nucleus, or AGN, that shines across enormous distances. These AGN are so luminous that they can outshine their entire galaxies, making them visible even from billions of light years away. The radiation and winds from such activity can blow out gas from the galaxy, shutting down star formation and determining how the galaxy will evolve in the future. In galaxy clusters, this kind of influence can spread even farther, affecting not only the central galaxy but also its neighbours through the flow of hot gas and radiation. The energy released by a supermassive black hole comes from the matter falling into it, but not all that matter disappears forever. Some of it is converted into radiation, while some is expelled in powerful outflows. The efficiency of this process is astonishing. Even a small amount of matter can release vast amounts of energy when it is compressed by the black hole's gravity. The accretion disk, which forms from gas swirling toward the black hole, heats up to millions of degrees, producing X-rays and gamma rays that travel outward. Magnetic fields in the disk twist and reconnect, launching twin jets in opposite directions. These jets carry energy far from the black hole, spreading it throughout the cluster. In this way, a single object only a few light hours across can affect regions millions of light years wide. Astronomers have used X-ray and radio observations to map these effects in great detail. In clusters like Perseus, they have seen ripples in the hot gas that resemble sound waves. These waves, generated by the periodic outbursts of the central black hole, carry energy outward, gradually heating the gas as they go. Each outburst acts like a heartbeat, keeping the cluster's core from cooling too much. Over hundreds of millions of years, this process prevents the formation of large cooling flows, streams of cold gas that would otherwise collapse into stars. It is an astonishing example of cosmic balance maintained by the hidden power of gravity and energy. In the case of the Phoenix cluster, located nearly 6 billion light-years away, astronomers have observed what may be one of the most extreme examples of black hole feedback ever recorded. The central galaxy in this cluster contains a supermassive black hole that has released an extraordinary outburst of energy, carving out enormous cavities in the surrounding hot gas. Yet, despite this, the cluster also shows evidence of intense star formation, suggesting that the balance between heating and cooling can shift under certain conditions. When the energy from the black hole weakens or the inflow of gas increases too quickly, the gas can cool faster than it can be reheated, leading to a burst of new stars. This reveals that black hole feedback is not always perfectly steady, but can vary greatly over time. The story of how black holes influence galaxy clusters stretches across cosmic history. In the early universe, just a few 100 million years after the Big Bang, the first black holes began to form from the collapse of massive stars. Some of these early black holes grew rapidly, fed by dense streams of gas, and became the seeds of supermassive black holes. As galaxies formed and merged, these central black holes grew larger and more active, shaping their surroundings through radiation and outflows. Over billions of years, as galaxy clusters took shape, their central black holes became the engines that controlled the temperature and structure of the intracluster medium. Even today, long after the most violent periods of growth, these black holes continue to shape the evolution of their environments. The influence of supermassive black holes extends beyond heating and star formation. Their jets and winds can also enrich the cluster's gas with heavy elements. When the jets plough through the surrounding medium, they stir and mix the gas, spreading elements such as iron, oxygen, and silicon that were forged in the hearts of stars. This enrichment process helps explain why the hot gas in clusters contains traces of these elements even far from the galaxies themselves. In essence, black holes help recycle material throughout the cluster, linking the life cycles of stars, galaxies, and the cosmic web. Supermassive black holes can also shape the appearance of galaxies on a large scale. Elliptical galaxies found at the centers of clusters are often smooth and featureless, with little evidence of recent star formation. This quiet appearance is not a sign of inactivity but rather of regulation. The energy from the central black hole has cleared out or heated much of the cold gas that could form new stars. In contrast, galaxies where the black hole is less active may still have spiral arms and ongoing star formation. Thus, the character of a galaxy is often a reflection of how active its central black hole has been. Over time, as clusters grow by merging with others, their central black holes may also come together. These mergers can create gravitational wave events of incredible power, detectable across vast distances. When two black holes merge, the new, larger one may recoil or spin rapidly, generating fresh jets and bursts of radiation. This activity injects new energy into the cluster's core, stirring the gas once again. The process shows that black hole influence is not limited to quiet heating, but can also involve violent energetic transformations that reshape the cluster's heart. Some of the most detailed simulations of galaxy cluster formation include the effects of supermassive black holes. Without them, the models produce clusters that cool too quickly and form too many stars. Only when black hole feedback is added does the picture match what astronomers actually observe. Clusters with hot, stable cores and limited star formation. These simulations show that black holes are not just small details in the cosmic landscape, but essential elements of how the universe builds large-scale structures. The energy produced by a black hole can take different forms. Sometimes it's mostly in radiation, such as light, X-rays and gamma rays, while other times it is carried by jets and winds. The balance between these forms depends on how quickly the black hole is feeding. When it consumes gas slowly, the energy is often dominated by jets, creating radio galaxies with large lobes of emission. When it feeds rapidly, it shines brightly as a quasar, producing intense radiation that can push gas away from the galaxy. Both modes have been observed in galaxy clusters, and both play important roles in regulating the surrounding gas. Astronomers have also discovered that black hole feedback can influence how galaxies within a cluster distribute themselves. The heating of the central gas can change the pressure and density of the cluster's core, affecting how smaller galaxies move through it. In some clusters, galaxies near the center appear to have lost much of their gas, likely stripped away by the hot medium that the black hole helps maintain. In others, the black hole's activity may compress nearby gas clouds, triggering bursts of star formation. Thus, the effects of a single object can ripple through an entire population of galaxies. Another fascinating aspect of black hole influence is the way it connects to magnetic fields. The jets and outflows from the black hole carry not only energy, but also strong magnetic fields that thread through the cluster. These fields can shape how gas moves and how cosmic rays spread through space. In some cases, they may even help confine the hot gas, preventing it from escaping the cluster. Observations of radio halos and relics, diffuse radio emissions found in many clusters, suggest that magnetic activity plays a key role in maintaining the structure and energy balance of the intracluster medium. Even the large-scale shape of a galaxy cluster can bear the marks of black hole activity. Some clusters show elongated cavities or chains of bubbles that trace the path of repeated jet outbursts. Each cycle leaves behind a signature of how the black hole interacted with its surroundings over millions of years. By studying these patterns, astronomers can reconstruct the history of a cluster's central engine and estimate how much energy it has released. In some extreme cases, such as the black hole in the cluster known as MS0735.6+7421, the total energy output is estimated to be equivalent to the explosion of hundreds of millions of supernovae, one of the most powerful events ever recorded in the universe. Despite their enormous influence, supermassive black holes occupy only a tiny fraction of the volume of a galaxy cluster. Their reach is not physical in size, but in energy. The radiation, jets, and winds they produce can shape regions millions of light-years away. This remarkable ability to affect their environment across such vast distances makes them one of the most important regulators in the cosmos. The interplay between gravity, heat, and feedback from these invisible giants ensures that galaxy clusters remain balanced systems, neither collapsing under their own weight nor exploding outward into emptiness. As observations become more detailed, especially with new instruments like the James Webb Space Telescope and the upcoming Athena X-ray Observatory, scientists are beginning to explore how this balance changes over time. They are now able to study black holes and clusters at much earlier stages in the universe's history, seeing how the first massive galaxies began to form and how their central black holes shaped their development. Each discovery adds to the understanding that these objects are not separate from their environments, but deeply connected to them, influencing everything from the smallest star to the largest cluster of galaxies. At the heart of the Phoenix, a galaxy cluster, lies an object of unimaginable size and power. A black hole so massive that even the largest known examples in the universe seem small beside it. This central black hole sits deep within the core of the Phoenix cluster, hidden beneath layers of blazing gas and swirling matter, yet its influence stretches across millions of light years. It is the true ruler of this immense galactic system, holding everything in place through the force of its gravity, shaping the behavior of entire galaxies and driving some of the most energetic events ever recorded in cosmic history. Black holes form when massive stars collapse under their own gravity, but the one at the center of Phoenix A is not a simple remnant of a dying star. It is a supermassive black hole, one of the largest kinds known to exist, with a mass that astronomers estimate to be in the tens of billions of times greater than that of our Sun. To grasp what this means, one can imagine that if this black hole were placed at the center of our Milky Way, it would outweigh Sagittarius A, the black hole at the heart of our own galaxy, by more than 1,000 times. While Sagittarius A has a mass of about 4 million suns, the black hole in Phoenix A may have a mass ranging anywhere between 20 billion and 60 billion suns. That is an extraordinary scale that defies normal human understanding. This colossal object is invisible by its very nature. No light can escape its pull, and so it cannot be seen directly. What gives away its presence is the light and energy from the material surrounding it. As matter falls toward this cosmic giant, it forms an accretion disk, a bright swirling ring of superheated gas and dust that glows with incredible intensity. This disk releases radiation across the spectrum, from visible light to powerful X-rays, allowing astronomers to detect and study the black hole indirectly. The discovery of this enormous black hole came from careful observations using multiple space-based and ground-based telescopes. Instruments like NASA's Chandra X-ray Observatory, the Hubble Space Telescope, and the Atacama Large Millimeter Submillimeter Array, known as ALMA in Chile, all played important roles in uncovering the secrets of the Phoenix cluster. Astronomers observed that the center of the cluster emitted unusually strong X-rays, far brighter than those seen in most other galaxy clusters. These X-rays revealed an immense source of heat and energy that could only come from the activities of a gigantic black hole feeding on surrounding matter. This black hole, located in the central galaxy of the Phoenix cluster known as Phoenix A, acts as both a creator and destroyer. Its gravity pulls in gas and dust from its surroundings, yet at the same time it blasts out enormous amounts of energy in the form of powerful jets and radiation. These jets can extend for hundreds of thousands of light years, tearing through space and heating the surrounding gas. The amount of energy being released is so tremendous that scientists believe this black hole has caused one of the most powerful outbursts ever observed in the universe, a blast so vast that it carved out giant cavities in the cluster's hot gas. These cavities, or bubbles, stretch across distances comparable to entire galaxies. They are the marks of the black hole's explosive activity, showing where its energy pushed away the surrounding material. Astronomers studying X-ray and radio maps of the Phoenix cluster have identified multiple such cavities, suggesting that the black hole has undergone several episodes of intense outbursts over millions of years. Each time, it likely swallowed huge amounts of gas and dust, only to release part of that energy back into its environment through violent jets. The mass of the central black hole in Phoenix A makes it one of the heaviest black holes ever discovered. Estimating such a mass is not an easy task, but astronomers can make calculations by studying the movement of stars and gas near the galaxy's center, as well as by measuring the brightness and size of the surrounding accretion disk. In the case of Phoenix A, the data suggests that the central black hole is at least tens of billions of times more massive than the Sun. To put this in perspective, the total mass of our entire Milky Way galaxy, including all its stars, planets, gas and dust, is estimated to be around 1 trillion solar masses. That means the Phoenix A black hole alone makes up a noticeable fraction of an entire galaxy's worth of matter, concentrated in a single, compact region of space. At the event horizon, the boundary beyond which nothing can escape the black hole's pull, the gravity would be so extreme that space and time themselves become warped. For a black hole of this mass, The event horizon could be wider than the orbit of Neptune around the Sun. That means the black hole's size could stretch across a distance of billions of kilometers. Yet all of this immense power and mass is packed into a region that, in cosmic terms, is still just a pinpoint. The behavior of this black hole is deeply connected to the structure and evolution of the Phoenix cluster itself. The energy released from its core activity regulates how gas cools and forms stars within the cluster. Normally, hot gas in galaxy clusters cools slowly over time, condensing to form new stars in the central galaxies. However, in many clusters, supermassive black holes prevent too much cooling by heating up the gas through their energetic outbursts. This process is known as feedback, and it helps maintain balance in the cluster environment. In the Phoenix cluster, though, this balance seems to be partially broken. The black hole has released immense amounts of energy, but the surrounding gas still cools rapidly and collapses to form new stars at an astonishing rate. The central galaxy of Phoenix A is one of the most actively star-forming galaxies in the known universe, creating hundreds of solar masses of new stars each year. The reason for this high star formation rate, despite the black hole's powerful feedback, remains a fascinating mystery. It may be that the black hole cycles between periods of intense activity and quieter phases, allowing cooling to occur in between. The central region of Phoenix A glows with extraordinary brightness across different wavelengths of light. Optical telescopes show clusters of young blue stars forming around the core, while infrared observations reveal massive clouds of dust and gas. X-ray images, meanwhile, display the hot plasma that fills the cluster, reaching temperatures of tens of millions of degrees. These observations together paint a picture of a galaxy both violently active and surprisingly fertile, one where destruction and creation go hand in hand under the influence of its central black hole. The jets produced by this black hole are particularly fascinating. They travel at nearly the speed of light and are composed of particles accelerated by the black hole's magnetic fields. As they shoot out from the poles of the accretion disk, they pierce through the surrounding gas and inflate large cavities in the hot plasma. These cavities can last for tens of millions of years before gradually collapsing or filling in again. The energy required to create such cavities is almost beyond comprehension, equivalent to billions of times the energy released by a supernova explosion. Astronomers have estimated that the total energy output from the central black hole's most powerful outburst could reach around 10 to the power of 61 ergs. That is roughly equivalent to the energy that our Sun would emit over its entire 10 billion year lifetime, all released in a single event lasting only a fraction of that time. This makes it one of the strongest known explosions in the observable universe, rivaling the most energetic quasars and active galactic nuclei ever seen. Such extreme power raises important questions about how these enormous black holes grow. Scientists believe that supermassive black holes like the one in Phoenix A form through the gradual accumulation of matter over billions of years. They begin as smaller black holes, perhaps only a few times the mass of the Sun, and then grow by merging with other black holes or by consuming large amounts of gas. However, the sheer size of the Phoenix A black hole suggests that it may have grown unusually fast, possibly during the early stages of the universe when galaxies were forming more actively and gas was more abundant. Some astronomers propose that black holes of this size could also result from a series of galactic mergers. As galaxies collide and combine, their central black holes spiral toward each other and eventually merge, forming a larger one. The Phoenix cluster, being a dense environment filled with hundreds of galaxies, would provide plenty of opportunities for such interactions. Over billions of years, repeated mergers could have allowed the central black hole to reach its current colossal size. Despite its terrifying power, this black hole plays an essential role in shaping the life of its host galaxy and the entire cluster. Without its feedback, the surrounding gas might cool too quickly, forming stars at an uncontrollable rate and exhausting the available material. On the other hand, if the black hole were too active, it could blow away all the gas and shut down star formation completely. Somehow, the Phoenix A system has found a delicate balance between these two extremes, resulting in a galaxy that both shines brightly with new stars and trembles under the force of its central monster. Observations show that the Phoenix A black hole is not constantly active. Instead, it appears to go through cycles of feeding and resting. During its active phases, it devours nearby gas, heating it up and sending out jets and radiation. This activity can last for tens of millions of years. Then, once the surrounding gas has been used up or pushed away, the black hole becomes quiet again, allowing the gas to cool and fall back toward the center. Eventually, the process begins again, creating a repeating pattern of outbursts over cosmic time. These cycles help explain the multiple cavities and shockwaves seen in X-ray images of the cluster's core. In the quiet periods, the central region cools enough for new stars to form. The gas condenses into dense clouds, collapsing under gravity to produce clusters of stars. The newly born stars shine brightly, giving the central galaxy its vivid blue appearance in optical images. This activity is so intense that the Phoenix cluster's central galaxy is considered a rare example of a cool core cluster that still manages to sustain massive star formation despite its active black hole. The relationship between the black hole and its host galaxy is one of constant interaction. The black hole feeds on the same gas that fuels star formation, and yet the energy it releases controls how much gas remains available for that process. This delicate connection, often referred to as the black hole galaxy feedback loop, is one of the key mechanisms that regulate the growth of galaxies throughout the universe. In the case of Phoenix A, this loop operates on an extreme scale, providing scientists with a unique laboratory for studying these cosmic processes in action. To understand just how extraordinary the Phoenix A black hole is, it helps to compare it with others known across the universe. The black hole in M87, a giant elliptical galaxy in the Virgo cluster, has a mass of about 6.5 billion suns and was famously imaged by the Event Horizon Telescope in 2019. The Phoenix. A black hole, on the other hand, could be several times heavier, possibly reaching 10 times that mass or more. If it were ever imaged in the same way, its shadow, the dark region caused by its event horizon, would appear vastly larger, though still distant and faint due to its location billions of light-years away. The light from the Phoenix cluster has travelled for roughly 5.7 billion years to reach Earth. That means when astronomers observe it today, they are seeing it as it was when the universe was less than half its current age. During that time, galaxies were still evolving rapidly, and clusters were growing through mergers and interactions. The central black hole of Phoenix A would have already been active back then, shaping the environment of the cluster as it continues to do even now. The Phoenix cluster itself is one of the most massive clusters known, containing thousands of galaxies and an enormous amount of hot gas. All of it is held together by the invisible glue of dark matter, which makes up most of its total mass. Yet at the very centre of this enormous structure, everything revolves, in a gravitational sense, around the supermassive black hole of Phoenix A. It is the anchor of the cluster's heart, the core that binds the surrounding galaxies and influences their behaviour through its radiation, heat, and gravitational force. The environment near the black hole is extreme beyond words. The temperatures in the accretion disk can reach millions of degrees, and the magnetic fields are so strong that they twist and channel matter into narrow streams moving at nearly the speed of light. These jets emit radio waves that can be detected from Earth, providing astronomers with another way to trace the black hole's activity. In fact, radio observations have revealed vast lobes of emission extending from the centre of Phoenix A, marking the paths of past outbursts that spread their energy across the cluster. Such intense activity affects not only the cluster's gas, but also its future evolution. The heat from the black hole's outburst can prevent gas from cooling fast enough to form stars in some regions, while in others, the shock waves might compress clouds of gas, triggering new star formation. This dual effect means that the black hole acts as both a destroyer and a creator on a cosmic scale. Even with all the data collected so far, many mysteries remain about this extraordinary object. How did it grow to such an immense size in the first place? How often does it erupt in these massive outbursts? How does it manage to sustain star formation in its galaxy while releasing so much energy? Astronomers continue to explore these questions through ongoing observations and computer simulations, hoping to better understand not just Phoenix A, but the general behaviour of the most powerful black holes in the cosmos. Some researchers have suggested that the Phoenix A black hole might be transitioning between different types of active galactic nuclei. It may have once been a quasar, a phase when black holes consume matter at extremely high rates and shine brighter than entire galaxies. Now it could be entering a more moderate phase, where the accretion is slower but still powerful enough to drive massive jets. Studying this transition could help scientists learn how galaxies evolve over cosmic time and why some become dormant while others remain active. If one were to look at the Phoenix cluster with human eyes, the black hole itself would remain invisible, but the surrounding galaxy would appear as a dazzling glowing mass of stars and hot gas. At its very core there would be a blindingly bright region, the accretion disk, radiating energy across space. Beyond that, faint jets of light and radio emission would stretch into the surrounding darkness, marking the immense reach of this cosmic engine. Over the coming decades, new observatories like the James Webb Space Telescope, the Square Kilometre Array, and future X-ray missions will continue to study the Phoenix Cluster and its central black hole in greater detail. These instruments will allow scientists to see deeper into the core, measure the motion of gas and stars more precisely, and perhaps even detect new evidence of how the black hole interacts with its environment. Each discovery will bring humanity closer to understanding how such colossal objects shape the universe on the larger scales. The event that astronomers later called the record-breaking explosion was one of the most powerful and extraordinary cosmic outbursts ever witnessed in the known universe. It was not a simple flare or an ordinary burst of energy, but something of an unimaginable scale, a gigantic cosmic eruption that far surpassed anything previously seen. The discovery came from the careful and patient eyes of astronomers studying a galaxy cluster known as Phoenix A, a colossal gathering of galaxies located deep in the southern constellation of Phoenix. The explosion was so enormous that even the scientists who first noticed its traces had difficulty believing what they were observing. It was like uncovering the scars of an ancient cosmic disaster, so large that it seemed to defy logic. The energy released in that single event was greater than anything produced by any known phenomenon in the observable universe, except the Big Bang itself. The first signs of this extraordinary explosion did not come from visible light, as one might expect, but from invisible waves of energy, X-rays and radio waves. These forms of radiation can pass through gas and dust that often hide distant objects from ordinary telescopes. Astronomers used some of the most sensitive instruments ever built, including NASA's Chandra X-ray Observatory, the European Space Agency's XMM Newton satellite, and radio telescopes from the Murchison Wide Field Array in Australia and the Giant Meter Wave Radio Telescope in India. The combined data from these instruments painted a picture that left scientists stunned. The central region of Phoenix A, which is home to a supermassive black hole, showed evidence of an enormous cavity carved into the surrounding hot gas. This cavity was so vast that it could hold hundreds of galaxies the size of the Milky Way. The sheer scale of it made astronomers realize that they were looking at the aftermath of a truly colossal explosion. The observations began when astronomers noticed unusual structures in X-ray images of Phoenix A. The gas within the cluster, which is typically millions of degrees hot and emits strong X-rays, appeared to be displaced in a strange pattern. There were large voids where the X-ray brightness dropped dramatically, and these voids extended across hundreds of thousands of light years. At first, the scientists thought it might be an artifact or a misreading of data, but after further analysis, the same pattern appeared in multiple observations from different telescopes. The shape of these cavities suggested that something powerful had blown through the cluster's core, pushing away massive amounts of gas and leaving behind empty regions. When the radio data were overlaid on the X-ray images, the pieces began to fit together perfectly. The radio waves revealed long plumes of emission, stretching outward from the center, corresponding exactly to the areas where the X-rays were faintest. This told astronomers that the cavities were filled with radio-emitting plasma, material that had been blasted out from near the black hole in a past eruption. As the researchers measured the size and extent of these structures, they realized they were dealing with an explosion of unimaginable power. To push out gas across such a vast distance required energy beyond comprehension. After many calculations, they concluded that the black hole at the center of Phoenix A must have released energy equivalent to hundreds of millions of supernovae exploding at once. In simple terms, if one could gather together all the energy from every star that exploded in our Milky Way over its lifetime, it would still not match what happened in that single outburst. This made it the most powerful explosion ever recorded in the universe outside of the Big Bang. The blast had ripped through the cluster's atmosphere, sending shock waves traveling outward at speeds of thousands of kilometers per second. Those waves heated and displaced the surrounding gas, altering the environment of the entire cluster. The size of the cavity alone told its own story. It stretched across about 1.5 million light-years, so wide that if you placed 50 Milky Way galaxies side by side, they would fit comfortably within the gap left by the explosion. The power required to create such a cavity was truly staggering. The black hole responsible for this eruption was feeding on vast amounts of gas from its surroundings. As the gas spiraled inward, it heated up and released energy in the form of jets, narrow, high-speed streams of particles moving at nearly the speed of the light. These jets punched through the surrounding gas, inflating huge bubbles of radioplasma. Over time, as the black hole continued to feed, the bubbles grew larger and larger, eventually creating the enormous cavities seen today. The radio telescopes captured these regions, glowing faintly in radio frequencies, revealing their shape and boundaries. To make matters even more incredible, astronomers found that the explosion must have lasted for tens of millions of years, continuing slowly but steadily over an extremely long period. The discovery of this explosion was not immediate. The data from Chandra and XMM Newton had been collected years earlier, but it took time and careful analysis to understand what they truly represented. The first researchers to notice the unusual cavities were studying the cooling flow of gas in the Phoenix cluster. In galaxy clusters, the hot gas between galaxies tends to radiate energy away, and over time it should cool and fall toward the center, where new stars can form. However, in most clusters, this cooling process is interrupted by the activity of the central black hole. The black hole releases bursts of energy that reheat the gas, preventing it from cooling completely. This delicate balance keeps the cluster stable. But in Phoenix A, something different had happened. The cooling flow was extremely strong, and the central galaxy was forming stars at an incredible rate, hundreds of times faster than in the Milky Way. This indicated that the black hole's feedback mechanism had somehow failed for a time, allowing vast amounts of gas to cool and fall inward. Eventually, the black hole consumed so much matter that it unleashed a violent outburst, effectively resetting the balance. When astronomers combined X-ray, radio, and optical data, they could trace the entire sequence of events that led to the explosion. The X-rays showed where the gas had been displaced, the radio waves revealed the jets and cavities, and the optical data captured the star-forming regions in the central galaxy. It became clear that the explosion had not destroyed the galaxy cluster, but had reshaped it. The energy released by the black hole spread throughout the cluster, preventing excessive cooling and star formation. This showed how supermassive black holes act as regulators of their environments, controlling the growth of galaxies through their enormous energy outputs. In the case of Phoenix A, that regulation had occurred in the most dramatic way possible. The power of the explosion was measured in terms of energy, and the result was astonishing. The researchers estimated that it released roughly 10 to the power of 54 joules of energy, an amount so large that it is almost beyond comprehension. To put it in perspective, the most powerful supernova ever recorded releases about 10 to the power of 44 joules. This means the Phoenix A explosion was about 10 billion times stronger than a supernova. Even compared to other known black hole outbursts, it was unmatched. For instance, a well-known event in the Ophiuchus cluster, which had previously held the record for the largest explosion, was only about one-third as powerful. The Phoenix A eruption surpassed it by a wide margin, setting a new cosmic record. Detecting such a vast explosion required years of patient study and the collaboration of multiple observatories across the world. The Chandra X-ray Observatory, orbiting above Earth since the year 1999, played a key role. Its sharp vision in the X-ray spectrum allowed astronomers to map the hot gas in the cluster with incredible detail. The XMM Newton satellite, launched in the same year by the European Space Agency, provided complementary data, helping confirm the presence and shape of the cavities. Meanwhile, the radio telescopes on Earth revealed the older, fainter emissions from the explosion's remnants. The Murchison Wide Field Array, located in Western Australia, specializes in detecting low-frequency radio waves, which are perfect for studying ancient cosmic structures. The giant meter-wave radio telescope in India, one of the largest of its kind, added further clarity to the picture. Together, these instruments gave astronomers a multi-layered view of the same event, like looking at different colors of light from the same source to understand its full character. The combination of data from these instruments allowed scientists to reconstruct the explosion's history. It began when the central black hole, which is estimated to be billions of times more massive than the Sun, started accreting vast quantities of gas. As the gas spiraled in, it heated up to extreme temperatures, producing enormous jets of energy that shot out from the black hole's poles. These jets travelled across hundreds of thousands of light years, ploughing through the surrounding material. Over millions of years, they inflated huge cavities in the cluster's gas, just like air inflates a balloon. When the jets finally stopped, they left behind these giant empty spaces that continued to rise slowly through the cluster's atmosphere. As they moved, they carried energy outward, distributing it across the cluster. This process of transferring energy helped stabilize the system by preventing too much gas from cooling and forming stars too rapidly. One of the most striking aspects of this discovery was the realization that such immense explosions can remain hidden for eons. Because the cavities expand slowly and the radio emission fades over time, the traces of ancient outbursts can be difficult to detect. The Phoenix A explosion happened hundreds of millions of years ago, yet its imprint is still visible today. The hot gas continues to bear the marks of that event, and the cavities remain as silent witnesses of a time when the black hole's power reached its peak. The study of these remnants not only reveals the scale of the explosion, but also helps scientists understand how energy flows within galaxy clusters over cosmic timescales. As astronomers analysed the data more deeply, they found that the explosion's influence extended far beyond the central region. The shockwaves it generated travelled outward for hundreds of thousands of light years, compressing and heating the gas in their path. In some regions, the compression may have triggered bursts of new star formation, while in others it may have prevented gas from cooling at all. This complex interplay between heating and cooling is one of the key factors that shape the evolution of galaxy clusters. The Phoenix A event provided a rare opportunity to study this balance in action on a grand scale. The detection of this explosion also demonstrated the importance of multi-wavelength astronomy, the practice of observing the same object in different kinds of light. Each type of radiation tells a different part of the story. X-rays reveal the hot gas, radio waves show the jets and cavities, and optical light traces the stars and galaxies themselves. Without combining all of these observations, the true nature of the event might have remained hidden. The fact that scientists could uncover such an ancient and vast explosion shows how far modern astronomy has come. It also highlights the power of collaboration between international teams and instruments. In addition to its scale, the Phoenix A explosion stands out for how much it teaches about the behavior of supermassive black holes. These objects, despite their name, are not simple consumers of matter. They are engines of creation and destruction, capable of influencing entire clusters of galaxies. When they feed slowly, they emit steady jets that shape their surroundings gently. But when they are overfed, as in the case of Phoenix A, they erupt with overwhelming power, releasing more energy than all the stars in their host galaxies combined. The Phoenix A outburst shows what happens when a black hole reaches that extreme state. It also helps scientists understand how feedback from black holes prevents galaxies from growing uncontrollably large. As the story of the Phoenix A explosion spread through the scientific community, it captured the imagination of researchers and the public alike. It reminded everyone that the universe still holds events of staggering power beyond what we can easily comprehend. Even after decades of studying black holes and galaxy clusters, astronomers continue to find surprises that challenge their understanding of cosmic physics. The Phoenix A explosion was one such surprise, rewriting the limits of what was thought possible. Some researchers compared the energy released to that of the most powerful known explosions, and none came close. The only event that could rival it was the creation of the universe itself, the Big Bang. The Phoenix A outburst was, in cosmic terms, a miniature version of that original explosion, reshaping its corner of the universe in an instant. Yet, unlike the Big Bang, it was driven not by the birth of space and time, but by the insatiable hunger of a single black hole deep within a cluster of galaxies. To make sense of how such an explosion could occur, scientists turned to simulations and computer models. These models showed that when a black hole grows rapidly by swallowing massive amounts of gas, it can release a sudden burst of energy through its magnetic fields. The energy escapes along the black hole's rotational axis, forming twin jets that blast through surrounding material. Over millions of years, these jets inflate the cavities observed in X-ray and radio images. Eventually, the gas supply decreases, the black hole quiets down, and the outburst ends. What remains is a cluster filled with the afterglow of the event, a cosmic fossil of extraordinary violence. The Phoenix A explosion is not only a story of power, but also of balance. Without such eruptions, galaxy clusters would cool too quickly, leading to excessive star formation and instability. With them, the clusters remain in equilibrium for billions of years. The black hole acts like a cosmic regulator, maintaining the temperature and structure of its environment through periodic outbursts. The event recorded in Phoenix A was the most extreme example of this process ever found, showing that the universe has mechanisms to maintain its order even on the larger scales. In the years following the discovery, astronomers continued to study the remnants of the explosion in greater detail. They used newer instruments such as the Atacama Large Millimeter Submillimeter Array in Chile to look for traces of cold gas and dust that might have survived the outburst. These studies revealed that despite the violence of the event, some regions in the central galaxy continued to form stars. This showed that the black hole's power, though immense, did not completely halt the life cycle of the cluster. Instead, it transformed it, redistributing matter and energy in a complex dance that would shape its evolution for eons to come. As observations improved, scientists also realized that the Phoenix A explosion might not be a unique event. Similar, though smaller, outbursts have been found in other galaxy clusters, such as Perseus and Ophiuchus. These findings suggest that such explosions may be a common feature of the universe, occurring whenever a supermassive black hole grows too rapidly. The difference is that in Phoenix A, the scale was so much greater that it set a new standard for cosmic eruptions. The lessons learned from this discovery extend beyond astrophysics. They reveal the interconnected nature of the cosmos, where a single event in one galaxy can influence hundreds of others. The energy from the Phoenix A explosion continues to ripple through the cluster, affecting its gas, its stars, and its future evolution. Even though the event occurred hundreds of millions of years ago, its effects are still visible, allowing scientists to study it as though it happened yesterday on a cosmic clock. Every observation, every calculation, and every image taken of the Phoenix A cluster tells part of this extraordinary story. Astronomers have always been fascinated by the extraordinary power that lies at the heart of the universe, especially when it comes to explosions driven by supermassive black holes. Among these, the outburst from the center of the Phoenix A galaxy cluster has become one of the most astonishing events ever recorded. To understand the sheer magnitude of such a blast, astronomers needed to measure its energy in a way that was both precise and convincing. Doing so was far from simple. The explosion occurred hundreds of millions of light-years away, and its effects stretched across regions larger than the entire galaxies. Yet through years of work and advanced technology, scientists were able to uncover the incredible power released in that single, colossal event. Measuring that energy required a combination of space telescopes, X-ray detectors, radio observatories, and complex computer models that worked together to reveal just how violent and immense the eruption truly was. At the center of this study was the Chandra X-ray Observatory, one of the most advanced telescopes ever built for observing the universe in X-ray light. Chandra, launched in the year 1999, was designed to detect high-energy radiation emitted by some of the most extreme objects in space, such as black holes, neutron stars, and supernova remnants. When astronomers pointed Chandra toward the Phoenix cluster, they noticed huge cavities, gigantic empty bubbles, within the hot gas that fills the cluster. These cavities were carved out by powerful jets of material launched from the supermassive black hole at the center. The black hole's energy output had pushed aside the surrounding gas, leaving enormous regions of lower density that could be seen clearly in X-ray images. Measuring the size and depth of these cavities was one of the first steps in estimating the total amount of energy that had been released. The process was not as simple as looking at an image and guessing how large the cavities were. Astronomers had to use precise mathematical models to estimate their true volume, since the images only showed a two-dimensional projection of what were actually three-dimensional structures. To calculate this, they combined the observed X-ray data with information about the density and temperature of the gas surrounding the cavities. This allowed them to compute the amount of work done by the expanding jets as they forced their way through the cluster's hot atmosphere. Essentially, the black hole had acted like a cosmic piston, pushing vast quantities of material outward and heating the surrounding gas in the process. The energy required to do this was mind-boggling, on the order of hundreds of millions of trillions of joules, far exceeding the energy produced by any other explosion ever seen in space. But X-ray observations alone were not enough to paint the full picture. To truly understand how much power the black hole had unleashed, astronomers needed to combine data from other types of telescopes that could see the same region of space in different wavelengths of light. The Atacama Large Millimeter / Submillimeter Array, known as ALMA, played a crucial role here. Located in the high deserts of Chile, ALMA consists of dozens of radio antennas that can be arranged across distances of up to 16 kilometers. These antennas work together as a single giant instrument, capable of detecting faint radio signals from the cold gas and dust that often accompany energetic events in space. By studying the Phoenix cluster with ALMA, astronomers were able to detect vast clouds of cool molecular gas that were moving in response to the black hole's outburst. This provided additional evidence of how the explosion had affected its environment. The data showed that while the black hole's jets had heated much of the surrounding region, they had also compressed and cooled other areas, triggering new star formation in some parts of the cluster. The presence of both hot X-ray gas and cool radio-emitting clouds revealed a complex interaction between the black hole and its host cluster, one that could only be understood by combining multiple observations. Another vital piece of the puzzle came from the Very Large Array, or VLA, located in New Mexico. The VLA is one of the world's most powerful radio observatories, consisting of 27 dish antennas spread out across the plains. These antennas can be moved into different configurations to change the array's sensitivity and resolution. When astronomers observed Phoenix A with the VLA, they discovered enormous lobes of radio emission extending outward from the central galaxy. These lobes traced the paths of the jets launched by the black hole, showing where high-energy particles had been accelerated and where magnetic fields were strongest. By comparing the radio maps from the VLA with the X-ray images from Chandra, scientists could directly link the cavities seen in the hot gas to the regions of intense radio emission. This provided confirmation that the same jets which created the cavities were also responsible for producing powerful radio waves. With these two datasets combined, astronomers could estimate both the mechanical energy of the expanding cavities and the total radiative energy emitted by the jets. Together, they revealed a picture of unimaginable violence, a single outburst so powerful that it surpassed every other black hole eruption ever recorded. To translate these observations into a clear measure of energy, astronomers used a technique known as cavity power analysis. In this method, the energy required to create the observed cavities is estimated using the product of the gas pressure and the volume of each cavity. Once this energy is calculated, it can be divided by the estimated age of the cavity, that is, the time it took for the jets to inflate it, to find the rate at which energy was being released. The result gives the mechanical power of the outburst. In the case of Phoenix A, the numbers were staggering. The energy released was equivalent to the simultaneous explosion of hundreds of millions of supernovae. However, the challenge did not stop there. Determining the age of the cavities required yet another set of measurements. Astronomers had to estimate how fast the cavities were rising through the cluster's hot atmosphere. This was done by modelling their motion using equations of buoyancy, similar to how air bubbles rise through water. The larger the cavity and the denser the surrounding gas, the slower it would rise. By comparing these theoretical models with the observed shapes and positions of the cavities, astronomers could estimate how long ago the outburst had occurred. These calculations showed that the Phoenix A explosion had unfolded over tens of millions of years, meaning that the black hole had been releasing energy steadily over a very long period. Because no single measurement could capture the entire event, astronomers combined data from several wavelengths, X-ray, radio, optical, and even infrared, to cross-check their results. The optical data, obtained using telescopes such as the Hubble Space Telescope and the Gemini Observatory, helped them identify the galaxies that made up the cluster and map how their stars and gas were distributed. By studying how light was scattered and absorbed across these galaxies, astronomers could infer how the black hole's outburst had affected the cluster's structure on a large scale. Infrared observations added yet another layer of information. Instruments like the Spitzer Space Telescope detected the warm dust that had been heated by the blast. This dust emitted light in the infrared range, allowing scientists to measure how much of the black hole's energy had been absorbed and re-radiated by the surrounding material. These measurements revealed that while much of the energy had gone into heating, the hot gas visible in X-rays, a significant portion had also been absorbed by cooler material and later re-emitted at lower energies. All of these observations were then combined into a comprehensive model using powerful computer simulations. These simulations recreated the environment of the Phoenix cluster in 3 dimensions, including the distribution of gas, stars, and dark matter. They allowed astronomers to inject virtual jets of energy from the center, adjusting the parameters until the simulated cavities and radiation matched what had been observed. This approach made it possible to test different scenarios, such as how fast the jets were launched, how long they lasted, and how much mass they carried, and see which one best fit the real data. Through this process, astronomers found that the black hole at the center of Phoenix A must have released an amount of energy equivalent to hundreds of millions of trillions of times the annual energy output of our Sun. That level of power is almost beyond human comprehension. Even if every star in an entire galaxy exploded at once, it would still not equal the total energy that this single outburst produced. The measurements showed that the explosion had created cavities extending hundreds of thousands of light years from the cluster's center, making them some of the largest ever seen. The remarkable precision of these measurements depended heavily on the sensitivity of the instruments used. The Chandra X-ray Observatory, for instance, can detect variations in X-ray brightness as small as a few parts per million, allowing it to distinguish between slightly denser and slightly thinner regions of hot gas. This ability is crucial when studying distant clusters, where the signals are faint and easily lost in background noise. Similarly, the VLA and ALMA arrays rely on the technique of interferometry, where signals from multiple antennas are combined to create a single, high-resolution image. This makes it possible to detect structures that would otherwise be too small or faint to observe directly. Astronomers also use data from the European Space Agency's XMM Newton telescope to confirm Chandra's results. XMM Newton, which has a larger collecting area than Chandra, can measure the total X-ray flux more accurately, even though its images are less sharp. By comparing measurements from both observatories, scientists could reduce uncertainties and confirm that the cavities seen by Chandra were real, and not the result of background fluctuations. This careful cross-verification gave additional confidence in the final energy estimates. Even after all these techniques were applied, astronomers continued to refine their models by comparing Phoenix A to other well-studied clusters such as Perseus, Hydra A, and MS-07, 35.6 plus 7 421 and each of which had experienced powerful black hole outbursts in the past. By analysing similarities and differences among these clusters, scientists could check whether their methods were consistent. In every case, the same general pattern appeared. The size and shape of the X-ray cavities corresponded closely with the radio lobes, and the total energy required to inflate them matched the estimated power of the jets. What made Phoenix stand out was the sheer scale of everything. It was larger, more energetic, and more massive than any of the others. Some of the most detailed measurements came from studying the shock fronts created by the blast. These are regions where the rapidly expanding gas from the explosion collides with the surrounding material, compressing it and heating it up. Shock fronts can be seen as sharp edges in X-ray images, and by measuring their positions and temperatures, astronomers can estimate how fast they are moving. The speed of these shocks provides another independent measure of the energy released. In the case of Phoenix A, the shock fronts were moving at thousands of kilometers per second, suggesting an explosion of truly extreme power. Spectroscopy played an essential role as well. By analysing the spectrum of X-rays emitted by the gas, astronomers could determine its composition and temperature. Different elements emit X-rays at specific energies, so the presence of peaks in the spectrum corresponds to particular atoms such as iron, silicon, or oxygen. The relative strengths of these lines reveal how hot the gas is, and by comparing temperatures across different regions of the cluster, scientists could see how the blast had heated the environment unevenly. This temperature mapping helped refine their energy calculations even further. The use of gravitational lensing measurements also contributed to understanding the total mass distribution in the cluster. Since gravity bends light, astronomers could analyse how the light from background galaxies was distorted by the cluster's gravitational field. This helped determine how much mass was concentrated in the central regions and how much of it was dark matter. Knowing the mass distribution was important because it affected how the shock waves and cavities evolved over time. A denser cluster would require more energy to push its gas outward, which meant that the total power of the explosion had to be higher than initially estimated. In addition to space-based observatories, ground-based instruments like the Magellan telescopes and the Subaru telescope contributed valuable optical and near-infrared data. These observations allowed astronomers to trace the motion of galaxies within the cluster, helping to determine how the outburst had influenced the cluster's overall dynamics. The motions of galaxies can reveal how much the gravitational potential of the cluster has changed due to heating or cooling of the gas. In the case of Phoenix A, the galaxies appeared to be moving in slightly altered paths, suggesting that the black hole's eruption had redistributed mass within the cluster. Advanced computer modeling was indispensable in bringing all this data together. Scientists used supercomputers to run simulations involving billions of virtual particles, representing gas, dust, and dark matter. These simulations reproduced the conditions under which the jets were launched from the black hole's accretion disk. By adjusting the input parameters such as jet velocity, energy flux, and direction, the researchers could recreate the observed cavities, radio lobes, and shock fronts seen in the actual data. When the simulated results matched the observations, they could be confident that their energy estimates were accurate. These simulations showed that the black hole must have been accreting matter at an extraordinary rate before the explosion began. As gas and dust spiraled inward, enormous gravitational energy was converted into radiation and kinetic energy, which was then released through twin jets that pierced through the surrounding cluster gas. Measuring how much energy these jets carried was a key part of the analysis. By comparing the brightness and extent of the radio lobes to theoretical models of jet propagation, astronomers could estimate both the total energy content and the efficiency of the black hole in converting accreted mass into jet power. Interestingly, the Phoenix A outburst also provided clues about how energy from black holes helps regulate the growth of galaxy clusters. The measurements indicated that while the explosion released an enormous amount of power, it also prevented the surrounding gas from cooling too quickly. Without this heating effect, the gas would have cooled and condensed, forming new stars at a rapid rate. By injecting so much energy into the cluster's atmosphere, the black hole effectively slowed down star formation and stabilized the cluster's evolution. This self-regulating mechanism is something astronomers have observed in other clusters as well, but never on such an extreme scale. Throughout the process of measuring the blast's energy, astronomers faced several sources of uncertainty. The main challenge was determining the true shape and orientation of the cavities, since observations from Earth only show a projection on the sky. If a cavity is tilted relative to our line of sight, its apparent size will be smaller than its actual size, leading to an underestimate of the energy. To correct for this, scientists used statistical methods, analysing the likely range of orientations and calculating how each would affect the total energy estimate. They also compared results from different energy bands and instruments to ensure that systematic errors were minimised. Another complication arose from the fact that some of the energy released by the black hole is carried away by particles that are difficult to detect directly, such as cosmic rays or neutrinos. These particles can travel vast distances without interacting much with normal matter, meaning that a portion of the energy budget might remain hidden. To account for this, researchers considered theoretical models of particle acceleration and estimated how much energy might have gone into invisible forms. Even when taking these uncertainties into account, the Phoenix A outburst still stood out as the most powerful black hole explosion ever observed. Over time, the continued monitoring of the cluster allowed astronomers to refine their measurements even further. Each new observation added a layer of detail, whether it was the discovery of fainter radio lobes extending even farther from the center, or the detection of subtle ripples in the X-ray brightness that hinted at repeated smaller outbursts. These findings suggested that the black hole's activity might not have been a single event, but rather a series of eruptions over tens of millions of years. By summing the energy from all these individual episodes, scientists could explain the vast structures now seen in the cluster. The data from Phoenix A has become a benchmark for future studies of black hole feedback in galaxy clusters. The techniques developed to measure its energy, combining X-ray imaging, radio mapping, optical spectroscopy, and computer modeling, are now being applied to other clusters to see whether similar processes occur elsewhere. Each new observation adds to a growing understanding of how supermassive black holes shape the cosmos on the larger scales. What made the measurement of the Phoenix A blast's energy so remarkable was the way it pushed the limits of current technology. Instruments like Chandra, ALMA, and the VLA represent decades of engineering progress, allowing scientists to see and measure phenomena that were once beyond imagination. The precision required to detect faint X-rays from hundreds of millions of light-years away, and to translate them into concrete measurements of energy, speaks to how far observational astronomy has come. Even as the measurements became more precise, astronomers continued to test their interpretations using independent methods. Some teams used the Sunyaev-Zeldovich effect, a phenomenon where high-energy electrons in the cluster's gas scatter cosmic microwave background photons, slightly altering their energy. By measuring these distortions with instruments like the South Pole Telescope, researchers could estimate the pressure of the hot gas and cross-check it against the X-ray data. The results confirmed that the pressures derived from different methods matched closely, reinforcing confidence in the calculated energy output of the explosion. After the tremendous explosion that shook the Phoenix galaxy cluster, astronomers discovered something astonishing in the aftermath. Enormous cavities and vast shock waves stretching across regions larger than entire galaxies. These immense voids, carved out within the scorching gas that fills the cluster, became visible only through the sharp eyes of advanced space observatories. The energy of the eruption was so powerful that it punched gigantic holes into the hot X-ray emitting gas surrounding the cluster's core. These cavities stand as silent witnesses to an explosion that ranks among the most powerful cosmic events ever recorded, leaving behind marks that continue to tell the story of what happened in that distant corner of the universe. To understand what these cavities are, it is important to know that galaxy clusters are filled with a type of matter called intracluster gas, which is made of extremely hot plasma that shines brightly in X-rays. This gas forms a dense atmosphere around the galaxies within the cluster. When a supermassive black hole erupts, shooting out jets of high-energy particles at almost the speed of light, it pushes against this hot gas. Over time, the jets carve out hollow regions or bubbles that appear as cavities when viewed in X-ray images. These are not small gaps. They are cosmic voids on a scale that challenges the imagination. In the case of the Phoenix cluster, the cavities left behind are so vast that each could easily fit dozens of Milky Way-sized galaxies inside. The process that created these cavities began deep in the heart of the Phoenix cluster, where a black hole billions of times more massive than the Sun resides. This black hole, lying at the center of the cluster's brightest galaxy, once unleashed a blast of extraordinary power. The eruption sent out colossal jets of energy that plowed through the surrounding gas, displacing it and forming gigantic empty pockets. The pressure from the blast created ripples that expanded outward. These are the shock waves that astronomers can still detect even after hundreds of millions of years. These shock waves moved like cosmic tsunamis, disturbing everything in their path and heating up the gas even more. When scientists looked at this region using telescopes such as NASA's Chandra X-ray Observatory, the X-ray images revealed these cavities as dark spots within the glowing gas. The cavities do not emit X-rays because they contain much less dense material than the surrounding areas. They appear as black or dimmed areas surrounded by brighter gas, showing exactly where the eruption forced matter away. The shape of these cavities is not perfectly round. Some are elongated or stretched in one direction, indicating the direction of the original jet of energy from the black hole. The size of each cavity is almost beyond belief. Some of them are hundreds of thousands of light-years across. To put that into perspective, 1 light-year is nearly 10 trillion kilometers, so these cavities measure trillions upon trillions of kilometers in diameter. Astronomers estimate that the total volume of all the cavities combined could hold tens of millions of galaxies the size of the Milky Way. This gives a sense of just how violent the explosion must have been. The pressure required to push such massive amounts of gas outward was enormous, comparable to detonating millions of supernovae at once. The energy output of this event is said to be equivalent to hundreds of millions of times the energy released by all the stars in the Milky Way during the same period. It was, in every sense, a record-breaking outburst that transformed the cluster's internal structure. But the cavities are more than just empty spaces. They are filled with clues about what the black hole was doing during the explosion. Inside the cavities, astronomers believe there are remnants of the powerful jets that created them, streams of high-energy particles and magnetic fields that still emit faint radio signals. These signals can be detected by radio telescopes, and when combined with the X-ray data, they give scientists a fuller picture of what happened. In radio images, the same cavities that appear dark in X-rays glow brightly, confirming that they are indeed filled with energetic particles from the black hole's jets. This combination of X-ray and radio evidence provides one of the clearest examples of how black holes can shape their surroundings on a massive scale. The shock waves, on the other hand, tell a story of their own. When the eruption took place, the rapid expansion of the cavities sent out compression waves through the surrounding gas. These waves are similar to sound waves, but on a cosmic scale, they move through the thin plasma of the cluster, carrying energy outward. Although they move much slower than light, they can still travel hundreds of thousands of light years over millions of years. As they pass through the gas, they heat it up and redistribute energy throughout the cluster. In some regions, the shock waves compress the gas so much that it glows even brighter in X-rays, forming patterns that astronomers can detect. These waves are still visible today, frozen in the structure of the gas like ripples on a pond that has turned to stone. One of the most striking aspects of these cavities is their stability. Even though the eruption occurred hundreds of millions of years ago, the voids are still intact. This means the surrounding gas is dense enough to preserve the cavities without letting them collapse, yet not so dense that they would quickly refill. Scientists use complex computer simulations to model how such cavities form and how long they can survive. The results show that once created, these enormous bubbles can remain visible for hundreds of millions of years before gradually merging with the surrounding gas. During this time, they continue to influence the environment of the cluster, stirring the gas and preventing it from cooling too quickly. This last effect is very important for understanding how galaxy clusters evolve. The hot gas inside clusters tends to cool over time, which should cause it to condense and form new stars in the central galaxies. However, in many clusters, including Phoenix A, this process does not happen as rapidly as expected. The cavities and the energy released by the black hole play a major role in preventing the gas from cooling too fast. As the shock waves move outward and the cavities rise through the cluster, they carry heat with them, distributing it more evenly. This heating process, known as feedback, helps regulate the cluster's temperature and slows down the formation of new stars. Without it, the central galaxy would likely experience a massive burst of star formation, consuming vast amounts of gas. The Phoenix cluster, however, is special because it shows signs of both strong cooling and powerful feedback at the same time. The cavities are evidence of immense energy release, but astronomers have also detected high rates of star formation in the cluster's central galaxy. This means the feedback from the black hole, while intense, has not completely stopped the cooling flow. Instead, it has created a balance where the black hole's outbursts periodically reheat the gas, while the gas continues to cool and forms stars between eruptions. The cavities therefore represent not only scars from past violence, but also regulators of the ongoing life cycle of the cluster. To measure the size and energy of these cavities, scientists rely on detailed observations and calculations. They start by determining the volume of each cavity from X-ray images. Then they measure the pressure of the surrounding gas using temperature and density data. By multiplying the pressure by the volume, they estimate the total energy needed to create the cavity. In the Phoenix cluster, the results show that the explosion released energy equivalent to roughly 10 to the power of 55 joules, a figure so large it defies human comprehension. This energy is about 5 times greater than that of any previous known black hole eruption. The blast that produced the cavities was not a brief flare, but likely lasted tens of millions of years, gradually inflating the voids to their current size. Astronomers also examine the structure of the cavities to learn about the direction and duration of the black hole's jets. In Phoenix A, the cavities are aligned along a specific axis, suggesting that the jets were ejected symmetrically from the black hole's poles. Some smaller cavities closer to the center indicate that multiple outbursts occurred over time, each forming new bubbles while older ones drifted outward. This sequence of eruptions paints a picture of a black hole that repeatedly became active, releasing bursts of energy in cycles separated by millions of years. Over these cycles, the cavities grew, merged, and expanded to create the enormous voids observed today. As the cavities rose through the gas, they acted like giant balloons filled with hot, energetic plasma. The difference in density between the bubbles and the surrounding gas caused them to buoyantly rise, similar to air bubbles rising through water. This motion stirred the cluster's atmosphere, mixing cooler and hotter gas layers and spreading the energy from the explosion throughout the region. In doing so, the cavities helped to prevent the core of the cluster from cooling too much. Even now, long after the initial eruption, The effects of this motion can still be traced in the flow patterns of the gas observed by telescopes. In addition to the cavities visible in X-rays, astronomers also found signs of even larger, more distant cavities that may have been produced by earlier eruptions. These older voids are fainter and harder to detect, but their presence suggests that the black hole in Phoenix A has been active for billions of years, undergoing repeated cycles of outbursts and quiet periods. Each cycle left behind new cavities and waves that together shape the cluster's overall structure. The current set of cavities might just be the latest chapter in a long history of explosive activity. The shock waves from the explosion are equally impressive. They form vast spherical shells that expand through the cluster, compressing and heating the gas as they move. The energy carried by these waves is enough to heat the surrounding medium for hundreds of millions of years. In some regions, the waves interact with existing gas clouds, triggering turbulence and causing the gas to swirl and mix. These turbulent motions are thought to play an important role in maintaining the cluster's temperature balance. By redistributing heat and matter, they prevent the gas from cooling too rapidly and forming too many stars at once. In the Phoenix cluster, the size of the shockwave front is extraordinary. Observations suggest that it stretches over distances of more than 1 million light-years from the cluster's center. The strength of this wave is such that it would have produced an enormous burst of X-ray brightness when it first expanded, though now it has faded as it spread farther out. Scientists can still detect subtle temperature and density differences in the gas that mark where the wave passed. These differences act like fingerprints of the explosion, allowing astronomers to reconstruct the event's timeline and intensity. The study of these cavities and shock waves has revealed much about how energy from supermassive black holes is distributed on cosmic scales. What happens in the tiny region near the event horizon of a black hole, an area only a few times larger than our solar system, can affect an entire cluster of galaxies millions of light-years across. The Phoenix cluster shows this connection in dramatic detail. The black hole's jets, though originating from a point smaller than the distance between the Sun and its nearest stars, manage to move gas on scales that dwarf entire galaxies. This transformation of small-scale energy into large-scale motion is one of the most fascinating aspects of astrophysics. Furthermore, these cavities are not isolated phenomena. Astronomers have found similar structures in other galaxy clusters, such as Perseus, Hydra A, and MS 0735.6 plus 7421 DOS. But none match the scale of those in Phoenix A. In those clusters, the cavities are smaller, and the energy released is less by several factors. The Phoenix A cavities therefore represent the upper limit of what such explosions can achieve. By studying them, scientists hope to better understand how supermassive black holes regulate the growth of galaxies and the temperature of the universe's larger structures. The detailed mapping of these cavities requires combining data from multiple observatories. X-ray telescopes show the hot gas, radio telescopes trace the jets and relativistic particles, and optical telescopes reveal the distribution of galaxies. Together, these observations create a complete three-dimensional picture of the cavities. In this picture, the central galaxy appears surrounded by huge hollow lobes that extend for hundreds of thousands of light-years in both directions. The edges of these lobes are bordered by regions of compressed gas where the shock waves have piled up matter. Beyond them, the density gradually returns to normal. It is an awe-inspiring image of how one event can reshape a colossal portion of space. Inside the cavities themselves, the temperature and composition of the gas differ from the surrounding regions. The plasma within is much thinner, but contains energetic particles moving at nearly the speed of light. These particles emit radio waves that can be picked up even after millions of years. Over time, the energy of these particles decreases, and the cavities fade from view. However, even as they fade, they continue to influence the cluster's dynamics by maintaining turbulence and slowing cooling. Scientists have also discovered that these cavities can act as reservoirs for magnetic fields. The powerful jets that formed them carried magnetic energy, which became trapped inside the bubbles. These magnetic fields can remain stable for long periods, affecting how particles move and how heat is transferred within the cluster. In some cases, the fields may even help support the cavities against collapse by providing additional internal pressure. Understanding the magnetic properties of these structures helps astronomers learn more about how energy is stored and released in galaxy clusters. The size of the cavities in Phoenix A is so extreme that they challenge existing models of black hole behavior. The amount of energy required to inflate them suggests that the central black hole must have been accreting matter at an unusually high rate. During the eruption, it likely consumed vast quantities of gas and dust from its surroundings, converting part of that mass into energy. Only a fraction of the infalling matter actually entered the black hole. The rest was expelled in the form of powerful jets. These jets travelled at speeds approaching that of light, drilling through the cluster's gas and pushing it aside to form the cavities. The process may have continued for tens of millions of years before finally subsiding. Even now, the black hole at the centre of Phoenix A remains active, though not as violently as before. Observations show that it continues to emit weaker jets and radiation, suggesting that it is in a lower energy phase. The existing cavities may eventually be joined by new ones as the black hole undergoes future outbursts. In this way, the cluster evolves through a continuous cycle of explosions and quiet periods, with each eruption leaving behind new cavities and waves that build upon the old. The discovery of these cavities also sheds light on how astronomers detect such events, despite their great distances. The Phoenix cluster lies about 5.7 billion light-years away from Earth, meaning the light we see from it today began its journey when the universe was roughly 2/3 its current age. Across the vastness of the universe, many incredible events have taken place, but few have ever compared to the extraordinary outburst that came from the central black hole of the Phoenix A galaxy cluster. For many years, astronomers have studied violent cosmic explosions caused by supermassive black holes, yet none of them had ever witnessed something so powerful, so immense, and so utterly record-shattering. When this gigantic event was first observed, it instantly stood out as the most energetic and largest black hole eruption ever recorded. Its sheer magnitude dwarfed all previous examples of cosmic violence, pushing scientists to rethink what they believed possible about how much energy a single black hole could release into its surroundings. To truly understand how the outburst in Phoenix A surpasses all others, it is helpful to look back at what astronomers had discovered before. In the past, several black hole eruptions had amazed the scientific world. One of the most famous examples occurred in the galaxy cluster known as MS07 35.6 + 7 421, which lies roughly 2.6 billion light-years away. The eruption from the central black hole in that cluster had long held the record for the most powerful known explosion since the Big Bang. The outburst there released an amount of energy equivalent to hundreds of millions of supernovae exploding all at once. It created vast cavities in the surrounding gas, each one more than 600,000 light-years across, meaning they were larger than the entire Milky Way galaxy. For almost 2 decades, that incredible event was considered unmatched. Scientists believed it represented the very upper limit of what a black hole could do when feeding on enormous quantities of surrounding material. However, when astronomers began to examine the Phoenix A cluster using space-based X-ray telescopes and radio observatories, they found evidence of something far beyond what MS0735 had produced. The Phoenix A cluster, located nearly 5.7 billion light-years from Earth, contains hundreds of galaxies bound together by gravity and a massive core of hot gas. At the very centre sits a supermassive black hole, millions of times heavier than any known star. When it erupted, it released energy on a scale so large that even experienced scientists struggled to express it in ordinary numbers. The outburst carved out giant cavities within the surrounding gas, each one so huge that the entire Milky Way could fit inside one of them more than twice over. Astronomers calculated that the total energy released by this single eruption was roughly equivalent to hundreds of millions of supernova explosions. The total output measured about 10 times greater than that of the previous record holder, MS07 35.6 + 7 421. It was not merely the strongest black hole blast ever observed, but also one of the most powerful events ever recorded anywhere in the cosmos since the beginning of time. The blast from Phoenix A was so vast that it displaced an unimaginable amount of gas, pushing aside material equivalent to hundreds of billions of solar masses. It was as if the black hole had punched a hole into the surrounding cluster environment, creating an enormous bubble of empty space filled only with low-density plasma and radio waves. In past black hole eruptions, astronomers had seen cavities formed when jets of energetic particles were fired outward from the black hole's poles. These jets would pierce through the surrounding hot gas and push it aside, leaving behind balloon-like structures detectable in X-rays and radio waves. Yet none of those cavities had ever approached the enormous size of the ones seen in Phoenix A. The sheer dimensions of the cavities alone provided a clear clue that the outburst from Phoenix A was in a class of its own. The scientists who first studied the data could hardly believe their results. When they compared the Phoenix A eruption to the previous record holders, the numbers were overwhelming. It was about 5 times more energetic than the next largest event, and released energy equivalent to hundreds of thousands of times the total annual output of our Sun multiplied by billions. The power released in this single outburst would have been enough to shine with the brightness of all the stars in a large galaxy combined for millions of years. To detect such a massive event, astronomers combined observations from multiple instruments, including NASA's Chandra X-ray Observatory, the XMM Newton satellite from the European Space Agency, and the ground-based Very Large Array in New Mexico. Each telescope provided unique data. The X-ray observatories revealed the hot, glowing gas in the cluster and the gigantic cavities carved out within it, while the radio telescope detected the faint but extensive emission from the relativistic jets produced by the black hole. When they put all this information together, a detailed picture of the event began to emerge. Unlike ordinary explosions that last only moments, such as supernova, this black hole eruption unfolded over hundreds of millions of years. The Phoenix A black hole slowly but steadily released enormous energy as it accreted matter and launched twin jets that blasted through the cluster's hot gas. Over this incredibly long period, the jets inflated the vast cavities now visible in the X-ray images. The total distance across these cavities was estimated to be more than 1 million light-years, making them some of the largest individual structures ever associated with a single galactic event. In the case of previous black hole outbursts, such as those found in Perseus A or Hydra A clusters, the energy released was impressive but significantly smaller. For example, the eruption in the Perseus cluster produced cavities only about 25,000 light-years wide, and even though it released vast energy, it did not approach the scale of Phoenix A. The eruption from Hydra A was more powerful than Perseus, but still nowhere near the levels measured in Phoenix A. In fact, when astronomers placed all known major black hole outbursts on a chart comparing their total energy output, Phoenix A stood out as an enormous spike towering above all others. One reason Phoenix A's outburst was so extraordinary lies in the size of its central black hole. Estimates suggest that it contains several billion times the mass of the Sun. A black hole of that size can draw in and consume matter on a gigantic scale. When matter spirals into such a massive object, it heats up to extreme temperatures and emits enormous amounts of energy before crossing the event horizon. In Phoenix A, the inflowing gas may have triggered a runaway feeding process, releasing more power than astronomers had ever thought a single system could generate without completely destroying itself. When scientists examined the surrounding region, they noticed that the outburst had also had dramatic effects on the entire cluster. The blast heated the cluster's gas to extreme levels, but at the same time the central area showed signs of rapid cooling, which led to intense star formation in the central galaxy. This combination of heating and cooling, destruction and creation, made the Phoenix A event even more fascinating. The black hole had not only unleashed unimaginable power, but had also shaped the entire environment around it, possibly influencing the birth of new stars on a massive scale. Earlier black hole outbursts were known to regulate the growth of galaxies by heating surrounding gas and preventing it from collapsing to form new stars. However, the eruption in Phoenix A was so powerful that it seemed to have both halted and triggered star formation at once, creating a delicate balance between suppression and renewal. In this way, the Phoenix A event did not just surpass earlier explosions in size and energy, it also challenged the conventional understanding of how black holes interact with their host galaxies. To put the scale into perspective, the total energy released by the Phoenix A black hole's outburst is estimated to be around 10 to the power of 61 ergs. This number is so enormous that it is nearly impossible to visualize. By comparison, the energy released by the Sun over its entire 10 billion year lifetime is about 10 to the power of 51 ergs. That means the Phoenix A event emitted roughly 10 billion times more energy than the Sun will produce in its entire existence. Even compared to other large-scale cosmic events, such as gamma-ray bursts or supernova explosions, the Phoenix A outburst was tens of thousands to millions of times more energetic. When astronomers compare Phoenix A to other remarkable outbursts, such as the Fermi bubbles in the Milky Way or the outflows in the Centaurus galaxy, the difference becomes even more striking. The Fermi bubbles, for instance, are massive structures extending about 25,000 light-years above and below the Milky Way's centre. They are believed to have formed from a black hole eruption millions of years ago, but the energy involved in that event was tiny compared to Phoenix A, barely 1/1,000,000th as strong. The Phoenix A eruption was so large that if it had occurred in our own galaxy, it would have destroyed the Milky Way's structure completely, scattering stars and gas far into intergalactic space. In the cluster known as Ophiuchus, astronomers also found signs of a colossal explosion about 390 million light-years away. That event too was initially thought to be the largest ever observed. It released energy equal to the detonation of hundreds of thousands of supernovae. Yet even that spectacular blast is now overshadowed by Phoenix A, which released about 5 times more energy. The Phoenix A eruption therefore holds the title of the most powerful known black hole outburst ever recorded by humans. Another reason the Phoenix A outburst stands out is the incredible precision with which it was detected and analysed. Earlier eruptions were often studied with limited data or single instruments, which left many details uncertain. But the Phoenix A event was captured using some of the most advanced technology available. The combination of X-ray, optical, and radio data provided a complete view of the entire process, from the central jets to the vast cavities extending across the cluster. Astronomers could even estimate how long ago the explosion began, roughly a few 100 million years, and how it evolved over time. The data revealed that the eruption was not a single sudden blast, but rather a sustained release of energy lasting for an extremely long period. This steady, controlled release may explain how such a vast amount of energy could be emitted without completely blowing apart the surrounding galaxy cluster. Instead of one catastrophic detonation, the Phoenix A black hole appears to have acted like a cosmic engine, pumping energy into the cluster's gas layer by layer, carving out bubbles and cavities over eons. This mechanism resembles how previous black holes in other clusters behaved, but on a scale so much larger that it redefined the limits of astrophysical power. As astronomers compared Phoenix A's eruption to all known examples, they noticed several key differences. The cavities were larger, the energy output was greater, and the distance over which the black hole's influence extended was more than double that seen in any other system. The hot gas around Phoenix A glowed intensely in X-rays, while radio maps revealed long, faint jets extending outward over hundreds of thousands of light-years. This combination of immense cavities and long radio lobes indicated that the central engine had been active for an extraordinarily long period, continuously feeding energy into its environment. In the Hydra A cluster, for example, radio lobes extend about 400,000 light-years from the centre, and the total energy output is immense, yet still far below that of Phoenix A. Even the famous Perseus A, whose central black hole in the galaxy NGC 1275 produces stunning ripples in the surrounding hot gas, cannot match the size or energy of the Phoenix A cavities. Perseus A's waves and ripples span tens of thousands of light-years, while Phoenix A's extend over 1,000,000 light-years or more. The eruption in Phoenix A also helps scientists understand the extreme ends of black hole feedback, the process through which black holes inject energy into their surroundings. Feedback from black holes is known to regulate galaxy growth, control star formation, and shape the structure of galaxy clusters. But the Phoenix A event demonstrated that feedback can occur on levels previously unimaginable. It showed that even the largest, most massive clusters are not immune to being reshaped by their central engines. The sheer amount of energy involved suggests that black holes can profoundly affect regions of space, millions of light-years across, changing the temperature, density, and even the overall stability of the surrounding gas for billions of years. Comparing Phoenix A with past eruptions also offers insight into cosmic evolution. Each recorded black hole explosion represents a different stage in how galaxies and clusters develop. The Phoenix A cluster, with its record-breaking outburst, may represent an extreme example of how feedback operates in the early stages of cluster evolution. Its central galaxy is still actively forming stars at a high rate, suggesting that the feedback from the black hole is not entirely suppressive. Instead, it seems to drive cycles of cooling and heating, which may trigger bursts of new star formation followed by quiet periods. Before Phoenix A was discovered, astronomers assumed there was an upper limit to how powerful a black hole outburst could be. The energy released from MS 0735 had seemed impossible to exceed, but Phoenix A broke that boundary entirely, forcing researchers to reconsider what supermassive black holes are capable of. It also raised questions about how such an enormous release of energy could occur without destroying the black hole's accretion disk or shutting off its feeding process. Some theories suggest that the central black hole in Phoenix A may have undergone a special phase of extremely efficient energy conversion, turning a higher fraction of the infalling matter into radiation and jet power than usual. Other scientists proposed that a sudden inflow of dense gas triggered a runaway reaction, causing the jets to become more powerful than ever before. In such a scenario, magnetic fields surrounding the black hole might have acted like giant coils, focusing and accelerating the jets to near-light speeds. Whatever the exact mechanism, it is clear that the Phoenix A outburst stands as one of the most extraordinary examples of energy production in the universe. Even as astronomers continue to study Phoenix A, they use its data to refine models of galaxy cluster behavior. By comparing it to smaller outbursts in clusters like Perseus, Virgo, and Centaurus, they can better understand how black holes influence cosmic structures across different scales. In smaller clusters, the feedback tends to regulate star formation gently. In larger systems like Phoenix A, it can dominate the entire cluster, changing its temperature, brightness, and even its long-term evolution. The sheer extent of the cavities in Phoenix A also gives astronomers clues about how energy travels through the intergalactic medium. The edges of the cavities are surrounded by ripples, shock fronts, and regions of compressed gas, showing how the black hole's power propagates outward. These patterns resemble the ripples caused by smaller eruptions in clusters like Perseus, but in Phoenix A, they stretch across hundreds of thousands of light years, proving that the same basic physics operates at vastly different scales. If the Phoenix A eruption were translated into human terms, it would be equivalent to releasing all the energy generated by every star in every galaxy of the local universe, focused into a single location for millions of years. Such a comparison highlights just how far beyond ordinary comprehension this event truly is. Even among the most violent cosmic phenomena, it stands apart as a new standard of power. Since its discovery, the Phoenix A outburst has been studied in detail using multiple wavelengths of light. In visible light, the central galaxy appears unusually bright and blue due to the rapid birth of new stars. In infrared, astronomers see dust heated by starlight and by the central engine's radiation. In X-rays, the surrounding gas glows fiercely, revealing the vast empty bubbles that mark where the explosion pushed material away. And in radio waves, the long faint jets trace the path of energy flowing outward from the black hole. This combination of features paints a complete picture of how the eruption developed and how it continues to affect the cluster to this day. When astronomers compare Phoenix A to the earlier record holders, they see not only a difference in size and energy but also in influence. The MS 0735 outburst, while incredibly powerful, affected mainly the inner part of its cluster. The Phoenix A outburst, in contrast, reshaped an entire region more than 1 million light-years wide, heating vast volumes of gas and altering the cluster's long-term thermal balance. It is likely that the after-effects of this explosion will remain visible for billions of years, serving as a lasting record of the black hole's unimaginable power. Even though the universe has seen many explosive events, supernovae, gamma-ray bursts, and colliding neutron stars, none of them occur on scales comparable to black hole outbursts in galaxy clusters, and among all those, the Phoenix A explosion reigns supreme. It demonstrates the power locked within gravity itself, showing how the most mysterious objects in the universe can release energy that reshapes entire cosmic structures. As technology improves, astronomers expect to find other outbursts in distant clusters that may rival or even surpass Phoenix A. But for now, this event remains the champion. It stands as a monument to the forces that shape the universe. Scientists have developed a way to see what the human eye could never capture. To study the colossal and mysterious forces that shape galaxy clusters and the cosmic structures within them, astronomers rely on a network of observatories scattered across Earth and orbiting in space. Among these are the Chandra X-ray Observatory, XMM Newton, and a range of powerful radio telescopes. Each of these instruments is like a window that reveals a different layer of reality. Some show the blistering heat of X-rays, others trace the cold tendrils of radio waves left behind by ancient cosmic eruptions. When their data are combined, they provide a complete picture of phenomena so massive that they can reshape entire clusters of galaxies. The Phoenix Cluster, also known as Phoenix A, became one of the most remarkable subjects of this combined observational effort. This galaxy cluster, located in the southern constellation of Phoenix, is home to a black hole of unimaginable power. To understand what happened there, scientists did not rely on a single telescope. Instead, they combined results from several major observatories to piece together the full story. The process required years of patient observation, cross-checking and collaboration among hundreds of experts spread across the world. The Chandra X-ray Observatory, operated by NASA, played one of the most important roles in this study. Launched in the year 1999, Chandra was designed to detect X-rays from extremely hot regions of the universe, places where temperatures reach tens of millions of degrees. X-rays are a form of high-energy light that cannot be seen by the human eye or observed from the ground because Earth's atmosphere blocks them. By orbiting far above Earth's surface, Chandra can observe these powerful rays directly. The data it gathers helps scientists map out the energetic environment surrounding black holes, neutron stars, and supernova explosions. In the case of the Phoenix Cluster, Chandra's observations revealed something extraordinary. It detected vast cavities in the surrounding gas, enormous regions where material had been blasted away by violent outbursts from the central black hole. The shape and size of these cavities helped researchers estimate the amount of energy that must have been released to carve them out. The results were staggering. The explosion was so powerful that it dwarfed anything previously recorded, even the most energetic eruptions known from other galaxy clusters. It became clear that Phoenix A's central black hole was capable of releasing energy equivalent to hundreds of millions of supernovae. Yet, X-rays alone could not tell the entire story. To fully understand what had happened, scientists turned to another space-based observatory, the European Space Agency's XMM Newton. This satellite, launched the same year as Chandra, is one of the largest X-ray telescopes ever built. Its mirrors are designed to collect faint X-rays from distant parts of the universe, allowing astronomers to study both the structure and composition of the hot gas-filling galaxy clusters. XMM Newton's observations complemented those from Chandra perfectly. While Chandra has the sharpest vision in X-ray astronomy, capable of identifying tiny details in the structure of clusters, XMM Newton excels at detecting faint widespread X-ray emissions. This made it ideal for studying the overall temperature and density of the gas around Phoenix A. The combination of the two datasets gave astronomers an exceptionally detailed view. Chandra provided the precision, and XMM Newton supplied the broader context. Together, they revealed not just the scale of the outburst, but also how the heat from the explosion spread through the surrounding cluster. But the story did not stop there. Radio telescopes on Earth added another crucial layer of information. Unlike X-rays, which trace hot gas, radio waves reveal the presence of cold, charged particles spiraling around magnetic fields. When a black hole ejects jets of material at nearly the speed of light, these jets emit strong radio signals that can be detected across vast distances. By studying these radio emissions, scientists can trace the paths of the jets and see how far the black hole's influence extends. One of the main facilities used for this purpose was the Australia Telescope Compact Array, located in New South Wales. Because the Phoenix Cluster lies deep in the southern sky, this radio observatory had an ideal position to observe it. Using its network of large dishes spread across several kilometers, astronomers captured faint radio emissions from the region surrounding the black hole. What they found confirmed the X-ray data. Enormous radio lobes extended outward from the cluster's center, perfectly aligned with the cavities seen by Chandra. These lobes were formed by jets of plasma that had blasted through the surrounding gas, leaving behind vast empty bubbles. The radio data allowed scientists to calculate how much energy was carried by the jets. Combining that with the X-ray data from Chandra and XMM Newton gave them the full picture. The results showed that the central black hole in Phoenix A had unleashed an explosion so powerful that it pushed apart gas on a scale spanning hundreds of thousands of light years. The energy required to do this was estimated to be equivalent to the total output of hundreds of trillions of suns over millions of years. It was a record-breaking event, an eruption unlike anything astronomers had ever documented before. The beauty of combining these observatories lies in the way each one reveals something the others cannot. X-ray telescopes detect the hot gas that fills the space between galaxies, while radio telescopes trace the colder remnants of past eruptions. When viewed separately, each dataset tells only part of the story, but when merged, they show how the energy from the black hole's jets interacts with the surrounding gas, heating some regions, displacing others, and shaping the evolution of the entire galaxy cluster. The collaboration between Chandra and XMM Newton is a perfect example of how space science advances through cooperation. Both telescopes orbit Earth, but in very different paths. Chandra travels in a highly elliptical orbit, taking it almost 1/3 of the way to the Moon at its farthest point, which allows for long, uninterrupted observations of faint sources. XMM Newton, on the other hand, orbits in a slightly lower but still elongated path, allowing it to observe the same object for extended periods. Because of these complementary designs, astronomers can schedule simultaneous observations, comparing data in real time and ensuring that no transient or short-lived event goes unnoticed. The instruments aboard these telescopes are also masterpieces of engineering. Chandra uses 4 nested mirrors that gently reflect X-rays onto its detectors. These mirrors must be polished to an extraordinary level of precision. Any imperfection larger than a few atoms could distort the incoming X-rays. XMM Newton, meanwhile, contains 3 large telescopes, each made of 58 concentric mirrors. Together, they collect a vast amount of X-ray light, giving the satellite exceptional sensitivity. Radio telescopes work in a very different way. Instead of mirrors, they use large metal dishes that act like antennas, capturing radio waves from space. These signals are then processed by powerful computers that combine data from multiple dishes, simulating the effect of a much larger telescope. When several radio telescopes around the world observe the same target simultaneously, their data can be combined through a technique called interferometry. This method increases the resolution dramatically, allowing astronomers to see fine details that no single telescope could detect alone. This method was crucial in studying the Phoenix cluster. Observatories across different continents collaborated, combining their signals to achieve the highest possible precision. The result was a series of radio maps that revealed the faint outlines of the black hole's ancient outflows. These structures were not visible in X-rays, but they provided the missing link connecting the energy output from the black hole to the cavities seen by Chandra. Combining data from different wavelengths is not a simple process. X-rays, visible light and radio waves each require their own techniques of analysis and calibration. The instruments have different resolutions, different sensitivities, and even different ways of measuring time. To merge their data, astronomers must correct for these differences carefully. In many cases, the images must be aligned with extreme precision, matching features that appear in multiple wavelengths. This can take months or even years of work. But the reward is a far clearer understanding of how powerful cosmic events unfold. For the Phoenix cluster, the combined dataset revealed that the black hole had gone through multiple cycles of activity. Some radio structures corresponded to older outbursts, while the X-ray cavities matched more recent ones. This suggested that the black hole had erupted several times over the past hundreds of millions of years, each time injecting massive amounts of energy into the cluster's core. By comparing the sizes of the cavities and the faintness of the radio lobes, scientists could estimate the timing and strength of each event. It was as if they were reconstructing the history of a cosmic volcano that had erupted again and again. The collaboration between Chandra, XMM Newton and radio observatories also helped confirm the nature of the energy source. Alternative explanations such as supernova explosions or collisions between galaxies could not account for the sheer amount of energy released. Only the activity of a supermassive black hole could fit the data. The jets observed in radio wavelengths, aligned perfectly with the X-ray cavities, were unmistakable evidence of powerful outflows produced by matter falling into the black hole and being expelled at nearly the speed of light. In addition to these main observatories, data from other instruments also contributed to the study. Optical telescopes, such as those at the Gemini Observatory and the Magellan telescopes in Chile, provided visible light images of the galaxies in the cluster. These helped identify the exact location of the central galaxy hosting the black hole and showed how the surrounding galaxies were distributed. Infrared data from the Spitzer Space Telescope helped detect regions of cooler gas and dust, revealing areas where star formation was still occurring despite the intense environment. When all these observations were compared, astronomers could see how the black hole's activity affected the entire cluster, influencing not just the hot gas but also the galaxies themselves. The Phoenix cluster turned out to be a laboratory for studying the relationship between black holes and their environments. The combined observations demonstrated that even though black holes occupy only a tiny fraction of the total mass of a cluster, they can control its evolution through their immense energy output. By heating the surrounding gas, the black hole prevents it from cooling and forming new stars too quickly. This process, known as feedback, helps regulate the growth of galaxies over billions of years. Without it, galaxy clusters might evolve in completely different ways. Every observation adds another layer of understanding. Chandra and XMM Newton measure the heat and density of the gas. Radio telescopes trace the flow of plasma. Optical and infrared observatories reveal the distribution of stars and dust. By bringing all these together, astronomers can build a three-dimensional model of the cluster and its central black hole. This approach has become a standard method in modern astrophysics, allowing researchers to explore everything from nearby galaxies to the most distant quasars. The collaboration that studied the Phoenix cluster involved scientists from dozens of countries. Data were shared through international databases, and researchers spent years analysing it before publishing their results. This kind of teamwork shows how astronomy has become a truly global science. No single nation or telescope could have uncovered the full story of Phoenix A alone. Only through cooperation, coordination, and the combination of different instruments could the mystery of this record-breaking explosion be solved. The results also highlight the importance of long-term missions like Chandra and XMM Newton. Both telescopes have been operating for more than 2 decades, far exceeding their original design lifetimes. Their continued success depends on constant maintenance, software updates, and careful calibration. Because of this long operational history, astronomers can compare data taken years apart and detect changes over time. In the case of Phoenix A, this allowed scientists to study how the cavities and radiolobes evolved, slowly expanding outward as the energy from the black hole spread through the cluster. Radio observatories also continue to improve. New instruments such as the Atacama Large Millimeter/Submillimeter Array, ALMA, in Chile have provided even sharper radio observations of galaxy clusters. Although ALMA operates at shorter radio wavelengths than traditional arrays, its sensitivity to cold gas has helped detect the remnants of material falling back toward the black hole after earlier eruptions. These observations, combined with data from Chandra and XMM Newton, revealed a cycle of energy release and cooling, an ongoing dance between destruction and renewal that shapes the cluster over cosmic timescales. Each dataset brings new surprises. XMM Newton detected faint ripples in the X-ray emission, possibly caused by sound waves propagating through the cluster's hot gas, like the echo of the explosion that once tore through it. Chandra's sharp vision showed that these ripples extended over hundreds of thousands of light-years, carrying enough energy to heat the cluster's gas and prevent it from collapsing into new stars. Meanwhile, radio observations uncovered relic structures far beyond the central region, hinting at even older eruptions that occurred hundreds of millions of years earlier. The combined evidence paints a vivid picture of cosmic power. At the heart of Phoenix A lies a black hole billions of times more massive than the Sun. It draws in surrounding gas, heats it to incredible temperatures, and then launches enormous jets that pierce through the cluster's atmosphere. These jets inflate vast bubbles, displacing gas and sending shockwaves outward. Over time, the cavities expand, fade, and eventually rise through the cluster like bubbles in boiling water. The X-rays trace the heated gas, while the radio waves mark the trails of particles accelerated by the jets. The combination of both shows how energy travels from the smaller scales near the black hole to the larger structures spanning the cluster. Through all these observations, one of the most remarkable lessons is how the universe's most violent forces can also bring stability. Without the black hole's energy output, the gas in the cluster's core would cool rapidly, forming stars at an uncontrollable rate. But the periodic explosions heat the gas and regulate star formation, maintaining a balance over billions of years. This feedback mechanism, first observed in clusters like Perseus and now seen on an even grander scale in Phoenix A, has become a cornerstone of modern astrophysics. All of this understanding would have been impossible without the cooperation of multiple telescopes and observatories. Each instrument contributed a vital piece to the puzzle. Chandra's high-resolution images showed the fine details of the cavities. XMM Newton provided wide-field measurements of the surrounding gas, and radio telescopes revealed the jets and lobes that connected them. Together, their observations created a single, unified view of one of the most powerful events ever witnessed in the universe. The legacy of these combined observations goes far beyond the Phoenix cluster itself. The methods developed to merge X-ray and radio data have since been applied to many other clusters and galaxies. Astronomers now routinely use multi-wavelength observations to study phenomena ranging from merging galaxies to supermassive black holes at the centers of distant quasars. Each discovery builds on the same principle demonstrated by the Phoenix study, that no single instrument can capture the full complexity of the universe, but together they can reveal the hidden structure of cosmic events with astonishing clarity. Even today, as new observatories come online, the lessons from Chandra, XMM Newton, and the world's radio arrays remain essential. The upcoming Athena X-ray Observatory, scheduled for launch in the next decade, will build upon their legacy, offering even greater sensitivity and resolution. Future radio telescopes, such as the Square Kilometre Array, will provide detailed maps of cosmic jets stretching across millions of light-years. When these new instruments join the global network of observatories, they will continue the tradition of cooperation that made the study of Phoenix A such a milestone. The combined observations of the Phoenix cluster stand as a testament to human curiosity and ingenuity. By gathering light that spans the entire electromagnetic spectrum, from X-rays to radio waves, scientists transformed scattered signals into a coherent narrative about one of the universe's most powerful outbursts. Each telescope provided its own perspective, but together they unveiled a single truth, that even in the depths of space, where distances are measured in billions of light-years, the collaboration of human minds and machines can illuminate the darkest corners of the cosmos. At the center of most large galaxy clusters is a dominant galaxy, often called the brightest cluster galaxy, which houses a supermassive black hole weighing billions of times more than the Sun. Surrounding this galaxy is an enormous reservoir of hot gas known as the intracluster medium. This gas is heated to tens of millions of degrees, causing it to glow brightly in X-rays. However, even at such extreme temperatures, the gas slowly loses energy over time by emitting radiation. As it cools, it begins to sink inward toward the cluster's core. If this cooling continued without interruption, the gas would condense and form vast numbers of new stars. But this does not happen at the rate that astronomers once expected. Something prevents the gas from cooling too quickly, and that something is the black hole at the center. The cycle begins with cooling. As the hot gas radiates energy, it gradually loses pressure and begins to flow inward, like a slow cosmic drizzle toward the cluster's core. This inward movement brings more material close to the central galaxy and its black hole. As the gas moves closer, some of it is drawn into the gravitational pull of the supermassive black hole. When enough matter falls in, it triggers a violent phase of activity. The black hole awakens, releasing vast amounts of energy through powerful jets and radiation. These energetic outbursts can heat the surrounding gas, stopping or even reversing the cooling process. The energy released during one of these outbursts is almost beyond comprehension. In some cases, the total energy output equals the combined energy produced by billions of supernova explosions. This power does not come from the destruction of stars, but from the conversion of gravitational energy as matter falls toward the black hole. Instead of swallowing all the incoming gas, the black hole converts part of it into intense jets of charged particles that shoot out from its poles at nearly the speed of light. These jets travel vast distances, carving out enormous cavities or bubbles in the surrounding gas. The creation of these bubbles transfers energy into the intracluster medium, heating it and preventing further cooling. As these jets push through the gas, they also generate shock waves, ripples that move outward like the waves from a stone dropped into water. These shock waves spread heat across the cluster, helping to keep the gas from cooling too quickly in any one region. Over time, the cavities rise buoyantly through the surrounding medium, like hot air bubbles floating upward. As they move, they stir and mix the gas, spreading energy and maintaining the cluster's temperature balance. Eventually, the black hole's outburst subsides as it uses up most of the available fuel. When the supply of infalling gas drops, the jets weaken, and the system becomes quiet once again. During this quiet phase, the hot gas begins to cool and drift inward again, restarting the cycle. Thus, the process repeats itself. Cooling draws material toward the center, feeding the black hole, which in turn heats the gas through violent outbursts, and the balance between the two maintains the cluster's stability. This cycle of cooling and heating is not quick. It unfolds over tens or even hundreds of millions of years, meaning that the clusters evolve slowly and maintain their structure for billions of years. If the heating were too weak, the gas would cool rapidly, leading to bursts of star formation that would dramatically alter the cluster's appearance. If the heating were too strong, it would blow the gas away entirely, leaving the galaxy starved of the material needed to form new stars. The black hole therefore acts as a kind of natural regulator, adjusting the flow of energy to maintain a fragile balance. Astronomers have spent decades studying these cycles using telescopes that can detect X-rays and radio waves. X-ray observatories like NASA's Chandra X-ray Observatory and the European Space Agency's XMM Newton have been especially useful in showing how the hot gas behaves in detail. These instruments can reveal the temperature, density, and movement of the gas in and around galaxy clusters. In many clusters, astronomers have observed large, round cavities in the X-ray images where the gas appears to have been pushed aside. When these cavities are compared with radio observations, they line up perfectly with regions where powerful jets from the black hole have injected energy into the gas. One famous example is the Perseus cluster, located about 240 million light-years from Earth. In the center of this cluster lies the galaxy NGC 1275, which houses a supermassive black hole that has been actively influencing its environment for millions of years. X-ray images of the Perseus cluster show clear bubbles and ripples in the hot gas caused by repeated black hole outbursts. These features provide direct evidence of how the heating and cooling cycle works in real time. Each outburst leaves behind cavities that persist for tens of millions of years, slowly rising and dispersing energy. As new outbursts occur, fresh bubbles form, ensuring that the gas never cools completely. Another striking example is the Phoenix cluster, one of the most luminous and energetic galaxy clusters ever observed. In this system, astronomers discovered that the black hole at its center produces extremely powerful outbursts capable of injecting tremendous energy into the surrounding medium. Yet, despite this, the Phoenix cluster also shows signs of ongoing cooling and star formation, suggesting that the balance between heating and cooling is not perfectly stable. Instead, it seems to swing back and forth, with periods of strong heating followed by phases of cooling and star creation. This observation supports the idea that the feedback cycle is a self-regulating process, sometimes overshooting or undershooting the perfect balance, but always returning toward equilibrium. The interplay between cooling and heating has far-reaching consequences for how galaxies evolve within clusters. Because the hot gas in the intracluster medium serves as a massive reservoir of raw material, its temperature determines how much gas can condense to form new stars. If cooling dominates, galaxies grow rapidly, producing many bright young stars. If heating dominates, star formation slows or even stops, leading to galaxies filled with older, redder stars. By regulating the temperature of this gas, black hole outbursts effectively control the rate of star formation across the entire cluster. The effects are not limited to visible matter. The heating and stirring caused by black hole activity can also influence how dark matter and normal matter are distributed within the cluster. As the jets push through the gas and cavities rise, they redistribute energy and momentum, shaping the cluster's structure over time. Even the motion of galaxies within the cluster can be subtly affected by these massive feedback events. One of the challenges in studying these cycles is that they occur over cosmic timescales far longer than human lifetimes. Astronomers cannot watch an entire cycle unfold from start to finish, so they must piece together evidence from many different clusters at various stages of the process. Some clusters show signs of active heating, with bright radio jets and newly formed cavities. Others appear to be in quieter phases, where cooling dominates and the black hole is relatively inactive. By comparing these systems, scientists can reconstruct how the cycle evolves and estimate how much energy the black hole releases during each phase. Modern computer simulations have become a powerful tool for exploring these processes. By modeling the physics of gas, gravity, and black hole activity, researchers can create virtual galaxy clusters and watch how they develop over billions of years. These simulations show that even small variations in the timing or intensity of black hole outbursts can lead to large differences in the cluster's evolution. When the energy feedback is tuned just right, the simulated clusters match the ones observed in the universe, providing strong evidence that the cooling and heating cycle truly governs their structure. One of the most fascinating aspects of this process is how such enormous systems can maintain balance for so long. The distances involved are vast. Clusters can stretch across millions of light years, yet the activity of a single black hole smaller than our solar system can influence the entire structure. This delicate coordination between the smallest and largest scales in the universe is a striking reminder of how interconnected cosmic processes can be. Even within the same cluster, the heating and cooling are not uniform. Some regions may experience stronger heating due to nearby jet activity, while others may cool more rapidly. This patchy distribution leads to complex structures in the gas, including filaments, bubbles, and ripples. These features are visible in high-resolution X-ray images, showing a constantly changing landscape shaped by the invisible hand of the central black hole. There are also cases where the heating cannot keep up with the cooling, leading to bursts of renewed star formation in the central galaxy. In such cases, astronomers observe large amounts of cold molecular gas and clusters of newly formed stars near the core. This suggests that the feedback process, while generally effective, is not perfect and sometimes allows cooling to temporarily win. Over time, however, the black hole becomes active again and restores balance by releasing another wave of energy. These alternating periods of heating and cooling may explain why galaxy clusters have remained stable over billions of years. Without the regulating influence of black holes, the gas would have cooled long ago, forming stars at an unsustainable rate and drastically changing the cluster's appearance. The fact that we still observe massive amounts of hot gas in today's clusters means that the feedback mechanism has been operating efficiently since the early universe. Astronomers continue to study this process using new generations of telescopes. Future observatories, such as the Athena X-ray Observatory and the Square Kilometre Array Radio Telescope, will provide even more detailed views of how energy flows through these colossal systems. With better resolution and sensitivity, scientists will be able to measure the temperature changes, shockwave patterns, and gas movements caused by black hole outbursts with unprecedented accuracy. The cooling and heating cycles within galaxy clusters are among the most fascinating examples of nature's balance. They reveal that even the most destructive forces in the universe, black holes, can also serve as stabilizing agents, preventing chaos by keeping their cosmic environments in check. These cycles not only shape the fate of entire clusters, but also help explain why galaxies like our own Milky Way exist in their present form. Over cosmic time, countless such cycles have played out across the universe, maintaining the structures that fill the vast expanse of space and guiding the slow but steady evolution of galaxies within it.